So, assalamu alaikum and good morning. So, shall I proceed, Prof?
Yes, please.
Okay, thank you. Good morning. Welcome to our special lecture, Solar Photovoltaic System, Design and Grid Connected PV System, organized by the Faculty of Environmental Management, Prince of Songkla University, Thailand. Before I invite our speaker, I would like to inform you this meeting will be recording. If you have any special security, please turn off your camera. And please prepare your questions so you can ask after end of our session. So before I invite our speaker, let me introduce our speaker. He was born and brought in Bangladesh. After his higher secondary level, he got Monobushi Scholarship in Japan. He has done his diploma Gunma National College and Technology in Japan. He did his bachelor at Toyohashi University and Technology in Japan. And after that, master's and PhD in thin film base at Tokyo Institute and Technology. He pursued his postdoctoral fellowship at University South Florida, USA. He started his career at Motorola Semiconductor Company Limited in Japan. After that, in 2004, he moved to Malaysia and joined as a senior lecturer at Multimedia University in Malaysia. In 2006 until 2018, he worked as a professor at University Kabangsaan, Malaysia, and he developed his own solar photovoltaic lab. In 2018, he joined as a full-time professor, Institute of Sustainable Energy, University Tenaga Nasional. Not only that, he was selected twice a top 2% scientist by Stanford University, USA. He's an author and mentor. Not only that, he also involved a voluntary work, especially IEEE Malaysia. He have done many projects based on solar cell, and he published many articles. So please join me and welcome to Professor Dr. Nowshad Amin.
Thank you, Mr. Shariar. A very good morning there and also here. Thank you once again, Prince of Songkla University, for inviting me for this special lecture. Today, there will be two sessions. In the earlier session, there will be on solar photovoltaic system, which is a small scale, which we call it standalone. And then after the lunch, there will be another session on a different kind of design. Let me share my screen. I hope all of you can hear me and see my screen.
Yes, Prof. We can see your screen.
Okay, let me put it in this mode. I don't know how to remove this one. Okay, just put it here. Okay. So thank you for a generous introduction, Mr. Shariar. I'm glad that once again, Prince of Songkla University has invited me to share my knowledge on solar photovoltaic system, especially in two sessions. Like one is on grid connected and one is on standalone system. I belong to, in fact, right now I'm working under the College of Engineering and Institute of Sustainable Energy of University Tenaga Nasional. Okay. Let me start with our institute or with our university. It belongs to the Tenaga Nasional Berhad, which is the sole electricity utility company of West Malaysia. And we are located, as you know, the Malaysia has two parts, eastern part and western part. We are in the western side. And as you know, that Kuala Lumpur is also in the western side. We are just 26 kilometers, just apart from Kuala Lumpur city. So we are in between Kuala Lumpur city and Kuala Lumpur International Airport. And I work in both universities, here, University Tenaga Nasional, as a full-time professor, and also as an honorary professor in my previous university, which is called University Kebangsaan Malaysia, or National University of Malaysia. In UNITEM, there are 5 research institutes, which is focused on mainly energy-related research. As such, we have Institute of Sustainable Energy, where I am working on solar energy-related research here. So we have, apart from solar energy research, we have wind, biofuel, hybrid renewable energy resources, and also we are working on sustainability. So it's a quite good combination of different kind of aspects of renewable energy research under one entity. I'd like to acknowledge my research group. We have altogether more than 35 students, researchers, a young lecturer, and also which includes professors as well. In both universities, we get together to do our research on, especially on solar PV or solar photovoltaics. Okay, with that, I would like to start my today's first session, which is on standalone PV system. Okay, so you can see the aerial view of our university. This is the administration block and some of the teaching labs here, and some places that belong to the university here. First of all, I'll introduce some of our activity, then basic PV circuits. That PV means photovoltaics. What is photovoltaics? So I'll introduce that one then, and then talk about the components that is required to make the PV system. So that, I mean, any newcomer can really understand the PV systems and can really configure the PV system, can make the PV system by themselves. And the sizing algorithm, there are so many algorithms, but I will be just discussing one, so that we can learn at least one algorithm, so that we will be able to do like PV sizing for our own system. Finally, I will show some of the practical examples. Before I start, let me start with the photovoltaic effect. The photovoltaic effect is such that whenever sunshine falls on certain materials, and if the material has inbuilt voltage difference, and there happens some drift of electrons or flow of electron. So that was discovered by French physicist long before, almost 1826, by Edmond Becquerel. This effect was discovered, but it was not utilized until 1940s. So in 1940s, enthusiastically, the researchers were developing some devices that is called photovoltaic or solar cells, which is really utilizing the photovoltaic effect, through which we can convert sunlight directly into electricity, and we can configure the devices into different kind of ways, like flexible, semi-flexible, transparent, semi-transparent, etc. Beside the rigid ones. I can show you some of the lineups here. For example, the rigid one, you can see the rigid one, that this is very solid one. Also, this one is solid. Also, flexible solar cells, semi-transparent, then fully transparent. There are some of them are fully transparent. So these are now possible. So let me start with the history. First solar photovoltaic device was like, first one is like this one. Like it's a silicon-based PN junction. You can see the N-type silicon is covered by the P-type layer, and there are electrodes on this side and this side. And these three gentlemen from Bell Lab in 1940, I think around 1950, 46 or 47, they made like this their invention, and then in 1954 it was really taken by that time like attention, which shows that 6% efficient solar cell was possible, and this 6% efficient solar cell, even after 50 years, was showing at least 1.5%, as you can see here. As you can see here in some of the this one, like 1.5%. That means even after like roughly 60 or 50 or 60 years, the solar cell does not degrade that much. It is still usable. Let me share the solar cell principle, the photovoltaic effect principle, through a small video that I collected from NREL website. So from sun, we get photons as particles. Okay? So these photons are striking the solar system on a rooftop. The solar system consists of some panels, and these panels, each panel has solar cells. This one is one cell, roughly 156 square centimeter. It has two layers, negative layer and positive layer. I'm sorry, the language is in Malay, Malaysian language. So whenever a photon strikes the junction, so electron is energized and it is coming out through the circuit, and it goes back to the solar cell again. So this is the way the solar solar cell works under the sunlight. Once again, let me show the schematic that how the solar cell works. Solar cell is very tiny device. I mean, in terms of its cross section, you can say roughly nowadays roughly 100 micron, and in some cases is around 10 micron thickness. However, if you see the sunlight strikes on the front side and then it energizes the electron it energizes the electron in the direction that electron can come out and can be exhausted, can exhaust its energy through the appliances. And if we look at the p-n junction from the physics perspective, that there are p-type material and n-type material divided by a built-in potential, that is this like difference on the both sides. Potential difference is called the built-in potential, and this built-in potential is the main driving force of the electrons that flow outside. So this is what is needed, in fact, to drive the electrons out of the solar cell. So how can we understand the solar photovoltaic conversion efficiency? That means how much power it is falling on the solar cell and how much power it will be generated. Okay, the power which is coming in, we call it P in, which is coming from the sun. We have a calculation. We know that roughly 1 kilowatt hour per meter square is coming, or 100 milliwatt per centimeter square is coming. It is already well known that how much power is coming from the sun. So we have to now find out how much power it is getting out through the terminals from each cell. So if you take the ratio of this, then we can call this as a power conversion efficiency, or PCE, which will be in a percentile value, which is finally we show in a percentile value like 10%, 20%, which also means that how many photons are striking and how many electrons are coming out from a PV cell. So that is the ratio is used for photovoltaic conversion efficiency. Now I'm going to show you simple solar cell model. Solar cell is basically a p-n junction diode. So this is the diode characteristics in first quadrant of a Cartesian Prof system. So, and this is the diode current. This is the reverse saturation current, and you know that the voltage and everything, and the NKT, Boltzmann constant, and the temperature, absolute temperature, etc., etc. So now, whenever light strikes on that p-n junction, so it works as a constant current source. That like there is a constant current source. This is the JL. So JL is added in the equivalent circuit. So and then this first quadrant will move to the fourth quadrant. So this is the value of the conversion efficiency, and this is the current which is created. JL is created, but it's created in the opposite direction, not in the positive direction. Okay, so that's why there's a minus. So we have to find out how much current is created due to the illumination of the sunlight. However, if we include the losses like series loss and shunt resistance loss, which is shown here, there are losses. So we need shunt resistance loss or shunt resistance as high as possible, so that the electricity does not flow this way. and we need RS as low as possible so that there will be no consumption of electricity in this, so that the current will appear in this terminal, which was generated by the sunlight. So usually that doesn't happen. Of course, there are some loss in RS and RSH. So we have to consider all those losses, and the equation becomes this complicated. And from the behavior of the IV curve, we can understand how significant the loss is. For example, if the shape of this curve is slanted, then we say that, oh yeah, there is a series system loss, and also if the shape from this direction it deviates, then we say that current shunt resistance loss is severe. That's what I'm showing here. So, and also sometimes there is a back-to-back diode, we call it, which is also destroying the shape integrity of the IV curve. That's why back-to-back diode sometimes may be formed because of some of the losses. So the solar cell characteristics may be like this, as you see here. So now, what are the terms? For example, this is the first shape we saw. Now we have to find out in the fourth quadrant. This is the shape that we must understand, and there are some parameters we call PM, maximum power. Okay, that can be tracked from a solar cell is the multiplication of between the two parameters, voltage maximum times current maximum. This voltage maximum and current maximum can be found from this IV curve characteristics. And also there are another term called fill factor, which is the integrity factor of the diode shape. So we finally can understand the efficiency, which is denoted by eta, Greek letter eta, which is the comparison between power out over power in. And finally, if we elaborate it, then we find that P in is 1 kilowatt per meter square, as I mentioned before. And Vm times Im means we can also change into this equation, which can be found from the IV curve. So fill factor times VOC times ISC. Sorry. So there is efficiency, one of the terms that we learned, the efficiency, but efficiency is always measured under the standard test condition, which is called STC. STC means 25 degrees centigrade air mass. The mass of the air is 1.5 times. And then this incident solar power will be 1000 watt per meter square or 1 kilowatt per meter square. So this is the standard thing which we measure in our lab, but it is not the same case whenever this solar cell or solar panels are put into the field to produce electricity. That time, the efficiency, of course, the efficiency shows that initially how good the solar cell or solar panel is, but whenever it is in the ground to produce electricity, there might be many deviation from the standard conditions. For example, the sunlight may not be the standard one, the air mass may not be the standard one, and inclination of the sunlight, okay? So, and also temperature will be different. So in reality, we use another term called energy yield. Energy yield means how much energy we are getting from a solar system, which will be found from the ratio of electric energy generation over incident solar energy. The bottom denominator is fine, it's the same as we use, but the problem is the electric energy generation from the solar panels, that time will be influenced by many things. Okay? So energy yield matters more to anyone who owns solar PV systems. So I would like to make sure that I would like to remind you that efficiency is one term that we want to have a very good efficient solar cell, but it is not the practical situation. It is inside the lab when we measure, but it doesn't really help us. It just gives us some sort of like idea that if efficiency is bigger or greater, then we need a smaller space for the solar cell to be made. So I just would like to remind that one to you. Now, solar cell classification. The first solar cell was silicon based. This is the wafer based. Now it is around 200 micron. As you can see, the thickness of this wafer is around 200 micron, which is roughly 2 times of our hair diameter. Our hair is roughly 75 micron. And if you compare the first generation solar cell with the other generations, you can see that these are only roughly below 10 micron, like 7 microns, 3 microns, 2.5 micron, 2 micron, 1 micron, even 0.2 microns. So there are different kinds of solar cells now out there, which are really, really thin, even in someone is in nanometer order. So which uses roughly 1% of the material of crystalline silicon. Okay, sorry. Let me. Next is the classification of solar energy technology. First of all, I'm showing in terms of the cells that is available right now, either in lab scale or in commercial scale. So first generation solar cells, which was made by monocrystalline silicon materials, which has an efficiency range within 18 to 25% is shown here. Then other are following. The second generation roughly started, I think, 1970s. Okay, so there are different materials than silicon, like cadmium telluride, amorphous silicon, copper indium gallium selenide, and then very recently we got different variations of organic and inorganic structures. So we call perovskite, and then also we have multi-junction solar cells, gallium nitride based, gallium phosphide based, and also we should not forget the only solar cells are not everything, but we also have to take care of the controllers that stabilizes the solar photovoltaic voltage, or it balances everything. So we call them balance of system, and which includes controllers, inverters, etc. So before I start, like definition of something, like for example the cell. Now cell 3 watt peak to up to 7 watt peak. Okay, watt peak means under the direct sunlight, peak sunlight. So how much it will produce? It will produce 3 watt hour of this scale. Okay, it is roughly 15 centimeter by 15 centimeter. Okay, and then it started 3 watt peak, but now the efficiency is so high that at one cell you can get up to 7 watt peak. So whenever the cells are joined together and it is laminated, then we call it module or panel. Then module or panel can be designed this way to make array. Okay, the size increases from cell to module. The size is increasing, and then panel. Then panel to array is size is quite big, so it could be megawatt range. Okay, megawatt or gigawatt range nowadays. So solar cells can be in many colors. We have to change the anti-reflection coating to make a color variety, and also we can make semi-transparent so that light can come in. So we can make different ways. In fact, nowadays everything is possible, and we can put on top of like our rooftop, or even a carved rooftop. We can put that way, so it is quite adaptable. I'm showing some of the commercially available solar panels here. Like for example, here the silicon-based solar panels, like silicon, we call it HIT structure, 245 watt peak, and then cadmium telluride. It doesn't have any. It doesn't show any segregation. You cannot see any small cells here, because we have to cut into small pieces. In fact, we don't have the same way that we produce by silicon. That's the beauty of the second generation solar cell. This is also as cadmium telluride and also CIGS. You do not see like wafers, because first of all we make one single piece and then we cut into small pieces. This is other way around. So these are all marketed or commercially available solar panels, mostly first and second generation. Now let me start with the sorry, if I can show. Okay, PV systems. So there are 3 different kinds of PV systems. Usually we say possible, like for example, standalone. That means completely it is independent of the utility. That means we are independent. We do not need anything from any others. Okay, not generator, not even utility, nothing. So this is called standalone system. So we have a solar PV array, a few panels. We have controllers. We call it charge controller. We have battery, and then we have maybe inverter to use for AC loads, and maybe straightforward we can use for DC load. Okay. And second one is, I show this way, grid connected one, because usually I'll show this one today. So we have solar panels and we have just inverter. There is no need of battery. We just have a connection box to give to be connected to the utility. That means the electricity supplier. So during the daytime, I can sell or send electricity power to the supplier, and at night I can buy back. Right? There will be some contracts. Okay, that is called grid connected system. So we do not need any battery. But in between these two, there is one system called hybrid. So we have similar like this, but we also have we do not have the utility here, but we have genset or generator, diesel generator or windmill or something else, some other form of electric power generation system together with the solar PV. We call it hybrid system. So these two systems can be utilized in the remote places where the grid electricity is not reachable. So these are the system, but usually we use standalone or grid connected system, as we are very much familiar with these two. Okay. Now, once again, just to remind you, efficiency and yield, that efficiency matters whenever you are making in a small scale, but whenever you are deploying those energy, yield matters. That means in the field, whenever you are putting solar panels, how much energy you are getting per day or per year or something like that, per month, something like that. So that's why, but there are some like pros and cons. If the efficiency is higher, so you need less space. If you make the solar panel of that efficient solar cell, you need less space. So that is the thing, that only efficiency matters just to make it smaller in size. But in real practical field, maybe smaller size may not perform well, rather the big one, rather other material may perform well. So there are dilemma that we need to take care. Okay. So now I write this way that, that efficiency or yield depends on a few things, like for example, solar radiation. Solar radiation, of course, although we use 1 kilowatt per meter square value, but it is not the same for every corner of the whole world, right? So it varies. So solar radiation here in Malaysia, in Kuala Lumpur, is completely different than maybe 25 kilometers away from our place. And this solar radiation is completely different in your place, in your province. And solar radiation fluctuates because of the cloud and maybe rain. Okay, and then system power rating. This is called watt peak. As I mentioned, that this is the, like, you know, in power rating means is the efficiency. If efficiency is good, that means you are getting high conversion ratio. System ratio, again, solar cell, this is solar cell efficiency, or this is called power rating. But system efficiency, which includes other components like inverter efficiency, controller efficiency, battery efficiency, cable loss, all those things. So there are so many other practical parameters that need to be taken care of whenever we really try to make a good, efficient solar panel system. If you just simply think about the solar cell efficiency and then finally try to make the system for you, then you may not get the required output from this system, because it includes other matters also. Okay, so that is, you have to be very much careful. Next. So in available solar panels, there are, I just picked these photos from somewhere. There are so many different kinds of solar panels available commercially, but on the back side, you have to check on the back side, because every solar panels have their configuration written on the back side. So for example, someone has written that P max or power max at the maximum sunlight, it will produce through 230 watt-hour of energy. Okay, so voltage at maximum power will be 29 volt. Current at maximum power will be 7.93 amperes. So if you multiply these two, definitely it will be 230 watt. Okay, so it's very easy. And then this solar panel we use, in fact, to produce the solar system. So the system, as I mentioned before, is there are two different, mainly small scale standalone system, which needs only maybe inverter, battery bank, a controller, inverter, battery bank, and solar panel, and it is not connected to the grid. So this is these three components are okay for standalone, but for grid connected system we need this way. Okay, we do not need battery. In that case, we just need solar panel, a grid connected inverter and meter, and connection to the grid. So in fact, as I mentioned, that PV design, system design, is a combination of science and art. So how it is satisfying both things. Science means whenever we analyze the specific site information, calculate the power values, because we have to analyze the input sunlight, because whatever comes as input, it will convert into output. So when we analyze scientifically, we call it science is there. How about the art? Art is how we are the art of the beauty is that how realistically we can cater our need. So the system sizing, how we really do it. So there is the art, in fact. That's why we say that PV system design satisfies both design satisfy both science and art. So for grid tie systems, the most important initial consideration are customers' budget and available space. For grid tie, so you have to worry about your space on your rooftop, or if you have a ground or field to put solar panels. So, and also your budget. Whenever we do PV research, we say there are three kinds. Solar photovoltaic research, we say there are okay, sometimes there is a disruption here. Okay, PV research is categorically divided into three things. For example, system research. The PV system research can be, or system design can be done using some solar system related software called Homer, PVSys, PVSol, PVWorks. And if we do, this is the one, but if we do research on device, there are so many softwares. And material research also, there are some, like for example, PV materials, we can do research on first principles calculation, DFT, quantum espresso, those kind of softwares. But today I'd like to focus on this, like system research. System research or system calculation can be done by the software, but we need to understand what is the algorithm behind. That's why today I'll be giving you some idea about even with that system design, you can make your own calculator. We call it PV calculator. You can make use of Excel file, and you can put the equation inside, and you can find out your own calculator, and you can put your own values from your own place. Okay, first of all, as I previously mentioned, that there are two different system configuration available for PV systems. One is off the grid, that means which is not connected to the grid. So uses PV technology that are not connected to a utility grid. On grid uses PV technology that are connected to a utility grid. So there are two systems, okay, off grid and on grid. Now in this session, I'll be only talking about the off grid system, and then afternoon I will be talking about the on grid system, or we call it grid tied system. Grid connected system, although I'll be discussing later, but just to show that there is no need of battery. Okay, there's no need of battery, and whatever rooftop space you have, you just utilize the whole rooftop space according to your budget, and you just connect through some inverter, and you can sell the electricity whenever you are not using in the house. You are selling to the grid, and whenever you need the electricity, you can buy it back, and definitely there will be a contract between you and the utility. So in this case, what is the design consideration? As the main design consideration is about your budget. That means how much you can spend for your rooftop system. And that's it. And also your contract with the utility company. However, on the other hand, off-grid systems are really, in fact, PV systems started with off-grid solutions first because it was very small scale. So we started electrifying our small gadgets, maybe phone, like, the phone relay kind of thing, antenna relay kind of thing in the beginning. So it was very small scale usage. We didn't know that it could be used, it could be connected to the main grid, and it could be so big, like, in gigawatt range scale. So, so this is in the beginning, we started with off-grid use. So whatever I need, for example, I'm out of the grid, so I have to rely on PV systems. So I design my own system so I can be self-sufficient in electricity. Here, I would like to remind you that in an off-grid system, solar panels can be considered as a heart of human body. Controller or charge controller can be considered as a brain of a human body. And battery can be considered, or can be analogous of the stomach. So whenever your brain is functioning well, your stomach is full, and your heart is pumping well, then only then the system runs very well, or only then we, the human being, can really work efficiently, right? So that is what I say. So we need a combination of these three in an off-grid system, well synchronized, okay, well, I should say designed, so that we can get the best benefit from this system. So I think this is the best way to show that how important each component is in any off-grid or standalone PV system. Let me introduce you some of the components. We call it BOS, balance of system. Solar panel is there. It's not a part of the balance of system, but the controller, for example, is balance of system. Inverter is a balance of system, and then battery is balance of system. So these are the balance of systems, and also the cable are balance of system, but these are the loads. Okay, so charge controllers can be found in different sizes in terms of electrical rating. In fact, the power rating or current rating. In fact, usually. So can it cater like 10 ampere, 20 ampere, 30 ampere, 45 ampere, 60 ampere, something like that. And also the voltage, 12 volt, 24 volt, 48 volt, etc., etc. So then batteries can come into different shape. There are different batteries of different materials. Sorry. Sometimes batteries are basically lead-acid-based batteries, but also there could be batteries based on lithium iron phosphate or lithium lipo battery, a Leon battery. We call different kind of now lithium-based batteries, which are more efficient, which has more DOD, that means depth of discharge. We can discharge it to a greater depth in the battery reserve. So inverters are also electronic component that inverts from DC to AC or AC to DC in the both way. So we can nowadays inverter and charge controller are together. So sometimes we call it grid connected inverter. So we need just only one component for the grid tie system. Also, we can include in the BOS, balance of system, mounting structures. As you can see here, the structures are of aluminum, like it should be robust under harsh climate condition. So we can make different kind of structures, and the angle of the structure depends on the latitude of that particular place, so that it will always face towards the sunlight. Let me show some of the standalone PV systems here, like some of the PV systems that you can see very small scale, like only one panel. This one panel is enough for maybe this slum house that uses only one television and a few lamps at night. So I mean, these are all single panel system, we call it. And even in other places, like in India, we call single panel system. Like on the rooftop, we put this kind of panel, and I mean, the house can be self-sufficient with just only one panel, and or this kind of panel systems that will pull the water from underground, okay, with the help of solar electricity. Okay, there will be some pump. Okay, the pump needs energy, and these solar panels will give the energy to pull the water from underground. Also, solar systems in other places, with the help of this solar panel, this tailor shop in the village is working, or a small shop is there. Even a cart, vendor cart with a solar panel is working here, or large scale on rooftop system, or even we call it large scale solar farm, LSS. Okay, this big on the ground or on the rooftop system for lighting of the house. Okay. Okay. Now, let me move on. I just showed some pictures of the PV systems. PV systems can be utilized in some of the other innovative ways. For example, this kind of car, solar car. Usually in the university level, we have competitions among the different universities of the world. So we have dispatched, or we have shown these 3 models in Malaysia that I worked in. So this quite like, it is almost 20 some years old. This is maybe 10 years old. This is also around roughly 8 years old. 2012, almost 10 years old. So we have also developed different kind of solar car, and we have some experience. Also recently, what I did, I converted my small car, which is very small one, like 1000cc car. I just put solar panel system on the backside. I put 2 batteries, and I have a meter here. And on rooftop, I put the solar panel, so I can get the electricity stored on my back of the boot. And then what I use it for, so I use it for the air conditioning of the car. So at least that will help me to reduce the fuel consumption by that way. Okay, so I have some record. This is my pattern of production of the solar electricity, and this is the usage pattern. So it was found that I am producing more solar energy than I have been using it. Okay, it's like, for example, I was producing in that 2 months 18 kilowatt hour, I was using only roughly over 4 kilowatt hours. So I can make it a more efficient size, like not this big, maybe half of it will be fine to cater my car. Now, let me start with the real topic, the PV sizing for a standalone SAPV, standalone PV sizing. So usually PV sizing we do for rural electrification, like for example, in the rural area, they are completely disconnected from the utility. So we have to improve their socio-economic conditions by giving them electricity. And also, so we can help them by providing electricity and then change their environmental disaster that they use, for example, firewood to light, to lead their home. So all those things. So we can help them by electrifying. We can help the rural electrification, providing the small PV systems to different houses. But there is no single system that can cater the whole community. So you can you can make your own system by simply knowing some logic, simply knowing some algorithms. Okay, so there are different approaches. What are the approaches? Like we can use either database, like how much the sunlight is coming, how much is the shading, and also we can use that how much is the total energy coming in a day. We can use some calculators, we can use some spreadsheet, we can use some computer programming to do this PV sizing. But everything, of course, this programming is not generated all of a sudden. Definitely somebody has produced the this computer programming based on some algorithms. So today I'd like to give you some hints how the algorithm was produced to make a realistic, to make a more applicable solar system for rural places, wherever you stay. To start with, I always say that solar system or solar energy harvesting is quite analogous, quite similar to rainwater harvesting. Okay, solar energy harvesting is you're harvesting the sunlight into electricity, and rainwater, you're collecting the rainwater to make it a drinkable rainwater. So how do we do that? So if we consider rain as solar energy, so we say that we are using a conical shaped funnel, and we are collecting the rainwater which goes only through the funnel, but there is a filter because rainwater might contain some dust or all these things. So we use some filter so that we can filtrate the water. And finally, we have a conical flask or flask which is the container. So we store the water inside it. And maybe I just put a tap here. So whenever I need the water, I just open the tap and I can drink it. So this is the small system. So same thing. If now I change it to solar panel, for example, this filter paper is the solar panel, that whatever sunlight is coming through the solar panel only can be usable, but which is collected through the charge controller will be usable, and which the electricity is stored in the flask will be usable. And finally, what is the end product? The charge. Okay, the charge which is contained in the flask or in the battery is usable. And whenever I need, I just open or I just connect to my loads. I hope you understand this very simple and analogous thing that solar energy is pretty much similar to rainwater harvesting. So you just use your now logic. Okay, for example, you have huge rain, but you made your funnel and these filtering systems big, but your container is small. This is battery, this is charge controller, and this is the solar panel. Like for example, the filter paper is the solar panel. So you make filter paper this big and funnel this big, but your container is small, so it will overflow, right? So it is not a good system. Again, you have always huge rain, no matter what, and your funnel is a small, your filter paper is small, but you have a big container, a big battery. So this is also exaggerated, I should say. And it will be, water will be just a couple of inches high here. So it is not a good system. So these are the two bad systems. So there should be a nice, it should match well, I should say. It should match well. That, okay, the solar panel size, filter, the controller size, battery size. So they are the one that decides how much energy you can really store or can make it usable. That's why I say sizing is very important. This is the adding. So that's why I put like some of the remarks here. That think of your life on an island surrounded by sea or seawater, okay, which is not drinkable, and you need to depend on daily 4 hours of rainwater. Only there are 4 hours of different every day. There are 4 hours of rain, and you are getting the rainwater, but for your drinking and other purposes. Now you have to plan how to collect that rainwater, how to purify it, and how to store it, and how to keep it for 2-3 days if there is no rain for another 2-3 days. So this is completely same. So first of all, how to collect? We have to collect the sunlight through the solar panels. How to purify it? Purify through the charge controllers. How to store? Store through the batteries. And how to store for 2-3 days? So I have to increase the battery bank. So completely it is that way. It's quite analogous to that way. Then if we feel that way, then size your rainwater collecting funnel, filter paper, or filter clothing, storage pot or battery, whole supply network. So this is, after considering this, you can size, you can make bigger or smaller. So an optimization of the components is what we need to do. Okay, now you optimize. If the panel is big, so I have to search for a good controller, like the current, how much current it can cater or it can really use. So you have to look for those kind of components of balance of system. So let me start. There are 8 steps. Okay, this is one of the algorithm that we teach, but there are other algorithms also. This is not the only one. So this is quite like, it's academic, I should say. It's more academic rather than more realistic to, like, you just let's just buy solar panels and just match with that one. So this is very academic. That means it is trying to find out the best matches. Okay, so there are 8 steps to make a good solar system. Out of 8 steps, first of all, you have to understand that what is your daily requirement of energy, electrical energy. Okay, first, okay, I have to know how much drinking water I need. So accordingly, I'll make my filter. I'll make my jug or pot. So first of all, you have to understand your energy requirement. This is one. Okay, 2, 3, 4. Okay, this 2, 3, 4 is how big I have to make my pot, my reserve pot. Okay, or tank or battery. If you say that way in water, in rainwater harvesting, it is just about how to make big, or one tank or 2 tank or 3 tank. Okay, sizing the battery bank, battery capacity requirement. We have to find out that we have to find out how to wear the battery bank. So 2, 3, 4 is related to the battery bank, or for the rainwater harvesting. If you think that how the jug or pot or tank we should put and we should connect, something like that. Then number 5 and 6, it's about the filter. Okay, the filter paper, the sizing the PV array and calculate the PV array size. So 5 and 6 is related to filter size, filter paper size, or solar panel size, how big solar panel I need. Okay, number 7 is about the charge controller. Charge controller is the most, like, intelligent. I said there's the brain of the system, like how to control the flow of charges or electricity from here to there. So this is number 7. And finally, inverter, the boss. This is the one, inverter. So inverter is utilized whenever I have AC loads. If I don't have the AC load, I have only DC load, so I don't need any inverter. Everything is connected to the DC network. So you see that out of 8 steps, 1 is is just how much energy we need. 2, 3, 4 is for the battery bank sizing. 5, 6 is about the solar panel sizing. 7, 8 is for the boss. Boss means balance of system, boss means component sizing, like charge controller sizing and inverter sizing. Okay, so there are 8 steps. I hope it is clear to you. Now we'll move on. How to understand my daily requirement. Okay.
Yes, Prof. Prof, if you need, we can go for 10-minute break.
Okay, I think I will take another 10 minutes, then I'll go for break. Is it okay?
Okay.
Okay, first of all, okay, I think better I take the break now because of 11:50 now.
Yeah, we'll back 11 and
yeah,
you can drink coffee.
Okay, no problem. Thank you so much. Thank you. Okay,
Thank you.
Okay.
So all of you, please just stay with us. Maybe you can go for drink coffee. Thank you so much for your having with us. Hello, Prof.
Yes.
Yes,
you.
Prof, you can.
Okay, still 2 minutes, I think 1 minute to go. Okay, let me share once again. I got some question I already replied. Later on, I think I can take other questions also. Okay, let me share my screen once again. I think I stopped here. Okay. So first of all, I mentioned that first of all, in the 8 steps, there are 8 steps, right? Out of the 8 steps, the first step is to know how much is my energy requirement or electrical energy requirement. So first of all, you can make a Excel sheet or something that in the left-hand side, you just put the name of the AC load items, because usually we use the AC appliances. For example, you have a fridge, you have TV, you have LED lamps, and how many quantities, you have a stereo. I think people are no more having a stereo set. So how many, the quantity and what is the watt, okay, wattage of that one, and how many hours per day it is running. In fact, I didn't know that the fridge, although we are connecting it to the fridge 24 hours, only 11 hours or 12 hours, roughly half of it, or sometimes 1/3 of it, they are connected to the utility. Rest they just try to, like, it's more like intelligent device nowadays, our fridges, so they do not require 24 hours connect, like, energy supply, electricity supply. So they are using 11 hours in this case. So 7 days a week, the total how much they are using per week, and from that divide by 7, how much per day, what hours they're using per day. So finally, less than 3 kilowatt, okay, 2,956 watt hour per day it is consuming. That means less than 3 kilowatt, okay, kilowatt per hour per day. So which is a quite manageable, which is not a big load, every day if I need only 3 kilowatt hour, I think it's not a big load, okay. And if every day is 3 kilowatt, like, roughly in a month, 3 times 30, like 90 kilowatt hour or 90 units they'll be using, okay. or in a year, this much they'll be using, okay. I already gave those values. So now, starting, first of all, we have to understand the daily load, okay. As I mentioned, you have to add the losses, because this is the energy, the requirement, okay. Total power times usage hour is called watt hour, right? Divide with the efficiency. Efficiency, decimal point. If we divide, that means we need more, because we have to include the losses. If there is a loss, that means we need more energy. It's not straightforward. Sometimes, yes, we say efficiency is 80%. That means 0.8 you have to put here. So you will need more watt hour than this simple calculation. The simple calculation is just multiplying the how many watts, but we are not including the loss, because power loss. But usually, to be more reserved in calculation, we usually put 0.9, 0.8, at least 10%, 20% of the power loss happens in our network. Okay. So that's what it is saying, that establish the losses, determine the daily load demand, estimate the projected growths, if any. If I include, like, projected growth means if I add more lamps, more appliances, then we have to put those values also. But in this case, it is not whatever appliances I have. Okay. So then from here, we have to know energy requirement per day, maximum current, total power divided by system voltage. System voltage is something, we say the voltage is a system voltage. That means everyone is connected to that voltage. We have to make sure that the solar panel is connected to the charge controller by that voltage, and the charge controller is connected to the battery with that voltage. So if I take you, for example, system voltage is not straightforward. For example, this solar panel system is 24 volt is the output voltage, and DC load here is also 24 volt, here is also 24 volt. So we have to decide either 12 volt, 24 volt, or 48 volt system volt. But there are some logic behind it. If the load is below 3, it is below 1, we say 12 volt is fine. 1 to 3, when 1 kilowatt hour to 3 kilowatt hour, up to 3 kilowatt hour, we say 24 volt system is okay. If more than 24 volt, more than 3 kilowatt hour a day we are using, then we say, okay, it should be 48 volt, something like that. There are some. So this system voltage is something at which volt the components are connected. That is called system volt. So which could be, so we have to decide that system. For example, total power needed, what is the total power? And if I divide that by that system voltage, then we can know the total maximum current. Okay, so determine the system voltage. As I mentioned before, if the PV system is less than 1 kilowatt per day, 12 volt system is okay. If it is between 1 to 3 kilowatt hour per day, it is 12 volt, 24 volt. If it is greater than 3 kilowatt hour per day, then 48 volt. But also there are other options that you can connect. Choose and specify a suitable PV system volt by considering size of the charging current. The charging current is the one that comes from the solar panel to the battery, okay, through the charge controller. That is called charging current. Okay, charging current size depends on the available charge controllers. Also, you have to make sure that the charge controllers are available, but nowadays it's quite okay. Charge controllers, that means the controller electronic device that is the brain of the system. You have to make sure that that is available in the market. Next, number 3, determine charge required. Daily, how much water we need. Okay? If I say this way, it is more understandable, right? If I say, it says, determine charge required. How much charge we need every day. Okay, but if I say how much water we need every day, same. Okay, so how can you understand? Total energy required divided by PV system voltage is called the charge required. So this much charge we need ampere hour. Charge required is any ampere hour, not in ampere. Okay, not in current. Its current charge is ampere hour. Now 4, 5 is about the battery. Okay, so this much water I need. So how big the container should be? For example, every day I need this much current, this much water, 5 liters of water. But okay, if I need every day 5 liters water, how big the container should be? Because it's not straightforward. There are some limitations of the battery. We cannot, we cannot. For example, battery is a container. Let me show you. There's a container, the water bottle here in front of me. If I completely, I fill it up to this brink, okay, up to this level, and I'm free to drink up to this, right? I can simply drink this 1 liter of water. But in battery, it is not. The battery that we are using, we call it depth of discharge. We cannot discharge to the 100%. We have to keep, we call it either 50% or 40%, or we have to keep some charge here to make it alive. So that's why the batteries that we are using, lead acid battery, has a disadvantage. We cannot simply take away all the charges that we stored there. So that's the limitation, and that's why we have to have several battery banks. Okay, several battery like tanks, as you say. So battery capacity required. So to have, for example, I need 5 ampere hour of charge. So, but I need every day. And for example, next 2 days there will be no more sunlight coming. So autonomy is called autonomy. How many days autonomy? I need 3 days stored. Okay, so I have to put the autonomy 2 days or 3 days. If I put 2 days, including today, it's today, including today, 2 more days, there will be autonomy 3. We have to multiply 3. That means I need more water. Every day I need 5 liters of water, but for 3 days I need 15 liters of water. It's simply like that. So if you consider of the autonomy, that means I collect today, but I will not use next to, I will not collect. I cannot collect. Maybe there will be some like, the cloud or something like that. It's very cloudy. There will be foggy. Okay, there is no more current, no more sunlight. So I have to, store on the day 1. So you have to multiply with that one. Then maximum DOD, depth of discharge. As I mentioned, if you look at my bottle, this is the depth of discharge. Now the water level is here. This is called the battery can be only evacuated until this level. We call it depth of discharge. It is maybe 40% means 0.4, 50% means 0.5, 80% means 0.8. So nowadays the batteries that we are using, they are not 100% DOD. If it is 1, that means 100%. Okay, so we have to consider that limitation of the battery. That means we need more charge. We need more capacity to store. Charge required 5 ampere every day, ampere hour every day. We need the container bigger, okay, because we cannot simply take away all the charges that we stored. I hope you understand. If you don't understand, I will make you again clear. Okay. Sorry, I have runny nose, so sometimes I disconnect and try to get rid. Okay, next, number 5, select the battery to be used. There are batteries. Batteries, you have to understand the batteries as well. The batteries do not discharge at the same rate. Okay, so we have to buy some battery which has a good discharge rate at 20 degrees centigrade or 10 degrees centigrade. So there are some certain certain parameters for the battery also, and also the battery cells, 2-volt cell, 6-volt cell, 12-volt cell. So these are the battery parameters. And also at different temperature, there are different rate, and also battery number of cycles of recharging. If you discharge, okay, if you discharge less, okay, battery, if you discharge less, that means battery can last long. If you discharge more, battery may not last long. So there's also like some limitations in the battery. So you have to choose right battery, not only the battery bank, but also the battery's discharge rate. So you have to have a very good battery so that the discharge rate is good to match my requirement, because it has to supply that charge. It has to provide the charge from the battery, right? So this discharge rate depends on like temperature, on DOD, all those things. So you have to have a little bit of knowledge on the battery itself. I'm not giving everything today. I said that you have to be careful about the battery choice. You just simply cannot put any battery, because there is a limitation. Lead acid battery has some limitation. And then we have a lithium-ion battery, lithium-ion phosphate battery, and supercapacitors. Somebody just questioned me. The supercapacitors are for small usage, not for large scale yet. But many supercapacitors can be in the series and parallel connection. But still, I from my knowledge, I know that supercapacitors is a good option, but it's still not the sufficient option for large scale storage systems. Okay, next. After knowing that how big the battery is, now we have to understand the battery capacity, determine the battery bank capacity, how many tanks or how many batteries you need. So number of batteries in series, system voltage divided by nominal voltage of the battery. Batteries are like roughly 12 volt. So if the system volt is 24 volt, so 24 divided by 12, so we have to put 2 in series, okay, so that it is matching, the battery voltage-wise matching with the charge controller with the solar panel. And how many batteries should be in parallel? So battery capacity required, ampere hour, divided by selected battery capacity. Okay, how many selected battery capacities, like maybe is like 60 ampere hour or 100 ampere hour. So you need 300 ampere hours. So divide by 60 hour. That is 5 in parallel you have to put. So from every 5 parallel, it will come. The charges will be supplied. So it is a kind of tank network. Tank means like water storage tank network. It's not only one storage. Okay, so think that way. So in PV, we need several batteries. It's not only one tank. We said, oh, I make a battery, because it's not available. Batteries are being sold by their specification. Each battery has a capacity in ampere hour. It has a nominal voltage or output voltage, and also it has a discharge rate. So for that, we are making the battery it is not sizable as individual element, but if I can make in series and parallel, I can make big battery banks. So that is the difference between the water tank. Water tank, maybe you can get 1 liter water tank, 2 liter, 10 liter, 20 liter, something like, you can make different kind of water tanks. But in the battery, it is not possible, because battery has some more limitations or parameters that we have to really make sure. Okay, so from here, finally, how many batteries we need? Batteries in series and parallel, if we multiply, so we need the number of batteries, so we can we need, in fact. Now we know that we need 5 liter of water. We need maybe 10 or small containers, okay, of say 10. Now, how much solar panel we need, or how much water purification, like so-called the filter paper we need? What is the area size of the filter paper? Okay, that is what it is saying in the number 7. Determine the PV array output required. Okay, after we find the battery Okay, after we find the battery, okay, total charge required, for example, we need 5 ampere hour every day. Okay, 5 ampere hour every day we need, divided by battery charging efficiency. Maybe charging efficiency is not 100%, it's less than 100%. So we have to, again, we have to exaggerate it. We have to oversize it. We sometimes call it oversizing, because there is a loss. If I say I need 105 liter, I collect 5 liter, maybe in the batteries, because I have to put in the tank. I need, let's say, 1 liter. I put 1 liter, but whenever I am sending to the battery, maybe some milliliter is already somewhere lost. So, then I find that, no, it is up to here. So, no, I need 1 liter. So it is lost. So if I consider the loss, that means this considering the loss, it will be 1 liter always. So it's called that to be very much like, on the like a reserve side, that how much. So you just divide that charging efficiency. It could be 90% efficient charging efficiency, or 80%, 70%. Let's say roughly 90%. That 10% is lost. So that PV added requirement, it's not 5 liter or not 5 ampere hour, maybe 5.5 ampere hour. Okay, that is what that is how we now know the PV added or filter paper size. Filter paper size will be bigger. Now, this is the most important academic point of view. This is the most important slide where we are thinking cell by cell. Give me one more second. I have to. Sorry, I have running nose. In this case, because we already know how much the solar array size we require in watt peak, but we have to consider every loss. Okay, like PVs, we want to be very much realistic. So that's why, after knowing from the step 7, we just cannot simply multiply. We just don't say that this much PV array output we need. No, we have to consider the outside temperature is not 25 degrees centigrade. It is maybe around 32 degrees centigrade, and the PV panels, temperature goes up to 60 degrees centigrade sometimes. So we have to incorporate all those losses. For example, we have to find out temperature, cell temperature. We have to find out the derated value of the power output from the panel and derated value of the voltage output from the panel. These three, through this some kind of equation, we will find out, okay, these two. So we want to make sure that our solar panel size is as realistic as possible. It is not, we just simply do not buy, okay, I need a 5 watt peak or 10 watt peak or 100 watt peak panel from the previous step. I just buy it. No, because there are still, because that 5 watt, 10 watt peak is inside the lab. Now, outside the lab, the situation is completely different. The temperature is so high and it will degrade. There are some degradation. Okay, there are some power loss. Okay, so those power loss are included in these 3 steps. First of all, you have to find out the cell temperature of each. Okay, in a solar panel, you know that there are cells, right? A few 60 cells in a panel, sometimes 72 cells in a panel, sometimes, and more than now 144 cells, half-cut cells. So we want to know the cell temperature from this equation. After finding the cell temperature, we have to understand the power, okay, watt peak derated value by putting all those values that we found from here. There are some given, like for what is NOCT, normal operating cell temperature, what is gamma PMP, temperature duration factor in silicon solar cell, what is G, what is this, what is T, all those things. So we are putting all those value. Finally, we try to understand the derated value, that means the exaggerated power or requirement. And there's also the voltage. Voltage maybe is not 24 volt. Okay, maybe we need the derated power, and whenever we divide by power, this amperage, we may get some more voltage, which is the solar panel does not really give you that much volt. One panel does not give you like 12 volt or 24 volt. It may be giving you different kind of voltage because of the drop degradation. Okay, if you consider all this, then next is easy. So VMP derated is P derated over IMP, maximum power current. Okay, maximum power current at the maximum power current. So then determine the number of modules in series. So you need PV system voltage, we already decided, right? 48 volt, for example, or 24 volt. So you divide this by this number of modules in series. That means how many? Maybe sometimes it will come as a decimal value, like 1.5. That means we just put 2 panels. For example, if you do system voltage 24 volt, okay, but our derated value comes as like 18 volt. So what will be happening? Like 1.5. So we say no, 1.5 cannot. We cannot put one panel and another half panel. Just we better put 2 panels in series. Okay, because it should be as equal. The module PV module voltage should be as same as PV system voltage, as I mentioned before. And then now determine the PV module daily output. The output is like, if you know the total current of each one, like each panel, okay, or the total IMP from this one IMP. So if you multiply with the PSH, peak sun hour I have shown here. Sunlight, sun rises at 7 o'clock in Malaysia and sets around 7 p.m. in Malaysia. So this is kind of Gaussian distribution, right? But if we just integrate this into a block, so how many peak hours? That means it is highest is 1 kilowatt. Okay, how many peak hours we can think in a rectangular shape? Okay, so give me another second. I have. So how many peak sun hours we can consider? So it may be 4. In Malaysia, it's usually consider 4 peak sun hours, because although it's 12 hours from 7 a.m. to 7 p.m., but if you make a rectangle, if you integrate in a rectangle, the whole thing, so it will be around 4.5 or 4, sometimes 4.5, etc. Okay. Then next is total source. How many? Because it's direct conversion. So each solar module daily output is this much. So how much peak sun hours? So this much water we can collect. Every day, 4 hours of, for example, sunlight is given. So straightforward, 4 hours sunlight is converted into 4 hours of current. So you just multiply. If it is a number of 4 times IMP, maybe it's 7. So 28 ampere hours, something like that. So if you multiply 28 ampere hours, so we have to know that this 24 ampere hour, we have to divide each PV module. Okay, so we have to put the PV module in parallel, because each one will be supplying. We cannot just put one single so-called this paper, filter paper. Okay, we just put several filter papers. Okay, that's the concept. Do not put one big silver paper, because we cannot find related kind of like charge controller. So we better we just cut our big filter paper into small sizes, so that to really match with our electronics, with the funnel. Funnel is the charge controller, if I could make you easier in that way. Okay, so this is the way. Then finally to how many solar panels we need. Number of total module required is number of total module in parallel and in series. And then finally, peak capacity is the total number of this. So total one module is this. So how many modules we need? So we just multiply total number of modules times total number of this. So total watt peak will be determined by that. I think it was a little bit because you didn't see anything. Now let me show you one example. Okay, it will be very clear. Okay, this example says small remote home in Malaysia has 5 lamps, each rated 10 watt DC, operating for 4 hours, and a radio, just only 2, right? Radio, usually we do not use radio. 20 watt operating for 2 hours. Design at energy system, independent energy system. Okay, using the PV battery standard configuration with the following requirement. For example, PV system voltage is 12 volt DC, 4 hours, 4 days of autonomy we need. Battery DOD, only 20% we can consume, 80% we have to leave. Daily solar irradiation is 3.5 kilowatt hour. This or peak sun hour is 3.5. Okay, total the solar is 3 peak sun hour is 3.5, maximum ambient air temperature is 35 degrees centigrade, maximum irradiance is 920, DC equipment efficiency is 95%. So this is some given. So first of all, from this information, we understand we understand the total energy needed is 252 watt hours. So it is below 1 kilowatt peak. So 12 volt system is enough. So first of all, 12 volt system is enough. Now, how much current we need? 12 volt divided by that one. Like how much DC current we need? With 12, if you divide this one by 12, we need that this much DC current we need. Now, yes, the daily charge requirement is this 1121. If we total charge, sorry, this total charge 252 divided by 12 volts, so 21 ampere hour charge we need. That means this much, let's say this much water we need. We need 4 days autonomy. That means we have to multiply the 4, this amount, divided by DOD 0.2. So we need, in fact, more water because we have to keep it for 4 days. Okay, 1 day we need 21, but battery, in the battery you can only use 20%. So 80% should be in the battery. So we need more water because even though we put the battery, you cannot use it. And then battery selection, we put the battery 60 ampere hour battery, we put and 12 volt battery. So battery in series, because the system voltage is 12 and battery voltage is 12, that means in series only one battery is needed. Battery in parallel, there will be a lot of battery. Total charge required divided by each battery has 60 amperes, so there will be 8 batteries in parallel. After 8 batteries and one in series, that means total we need 8 batteries, and total battery bank capacity is 8 times 60 ampere hours, 460 ampere hour. Now PV size, because battery charging efficiency is only 90%. So determine the battery efficiency over daily charge requirement. So we need this much charge per daily, and then we use that equation to understand the total degraded value of each element. If we find out, then derated value of volt is 14.21 volt. So we know that this is system voltage is 12, but our PV voltage is 14 volt. So what to do? So it is so we can put only 0.8 panel, but we cannot put 0.8 panel. So we have to put 1 panel, nearest round-up value. And each one has 4 point this and 3 hours of sunlight, 3.5 hours of sunlight. So each one produces 15.89 ampere hour in a day. So how many we need? Total we need this divided by each one produced. That means we need 1.4 panels. Means 1.4 panels. We do not cut panels into 1.4, but nearest rounded value is 2. So we need 2 in parallel. So 2 in series, 2 in parallel, 1 in series. So we need two quantity of panels. Okay. So, and then we multiply because the solar panels available are 80 watt peak. So we just multiply these 2. So we have to use 160 watt peak solar panel. So we just put all the values here. Okay. So if you draw, we need 2 panels. Each one is 80 watt peak. We need 60 ampere hour, 8 battery banks in parallel, not in series. Okay. In parallel, and charge controller, 12 volt charge controller, distribution board, and then DC load. So the thing is already ready here. Okay, charge controller, distribution board, 2 panels in parallel, okay, and 8 battery in series. So this is not, I mean, just an example. This is not the realistic, the 8 panels, 8, just to have 4 days autonomy, you have to have 8 battery banks, which is too big. And the battery DOD is 0.2, which is also not good. That's why we need more batteries. Okay. Okay, I think so. Now, how about the other things? How about, for example, the diode, blocking diode, charge controller, inverter, cable, fuse, such protection device? We call it balance of system. Okay, such as controller, inverter, cables, batteries. So these are all battery balance of system. This balance of system we must utilize. Okay, we must utilize this balance of system. We have to also size it. Okay, we have to fix, like, for example, current rating, whatever the voltage rating, we just multiply the 2. So every bypass diode should have the rating matching with these values. So I'm just showing the balance of system, how big the cable is needed. So this is, I'm just skipping because this is the main sizing is done. This is just like subsidiary, let's say the secondary, in fact, secondary choices. How big this fuse should be used. Fuse should be 1.3 times of the fuse rating. We should use of the total power charge, total power. Okay, so this, so current, if it is current 5 amperes, so 5 times 1.3, like maybe 8 amperes fuse you have to use. Okay. However, after doing this, you can put all those as in one of the Excel sheet. Okay, you just put like in the Excel sheet, you can put you can make your own calculator by putting, like, you know, for example, what are the loads, and then step by step you can put, and you can make your own calculator. So I just shown whatever I have shown here. I just put is in a Excel calculator like this. Okay, so this is the system that how we connect. Okay, there is a system, 12-volt DC system, 750 watt peak, that like 5 panels, 150 times 5 means 750 watt peak standalone system. These are in series. Okay. Okay. Then fuse 6. I think these are sorry, these are not in series. These are in parallel. So these are giving 60 ampere of fuse, and then there is circuit control, circuit breaker. There are 2 batteries in parallel. This is the charge controller. Then there is a 1 inverter. So this is the most realistic drawing for the electrical engineers to make the solar system. Okay. So what is this charge controller? Is like, this is the charge controller, as you can see here, and the inverter. This is the grid off-grid inverter. Nowadays there are grid connected inverters. So this is what off-grid inverter, sine wave. We call it pure sine wave inverter. So here is this is the inverter. This one. Okay. So if you want to make it more complex, if you want to make your solar system together with others, you have to know how to connect. Like, for example, if you want to choose, you have a selector. Okay, I want to use the standalone system. I want to use the existing setup like this. So there are something more, the extended setup, that we call it, extended configuration. You can use also this way. Sorry. Recently, we have made one 3 kilowatt peak system. Okay, we call it solar cabin. This is a container. Okay, we put a 3 kilowatt peak panel, like roughly 12 panels here. 12 panels, each one is 265 watt peak. Okay, it is like with this configuration. Okay, so we just made it like 2 months ago. We just, like, this is this big. This is this big. So it's kind of a lab. Inside there will be a lab, but it is also a standalone lab. It is not connected to the grid. So it was delivered. Inside is like this big. You know, from outside you can see it is near our College of Engineering. This is the College of Engineering building. Okay. We have a Greens Park. We have a park called Greens Park. Okay, 3 kilowatt peak solar cabin at Greens Park. The park is called Greens Park. So we just put a little bit elevated. Okay, if there's, so that there's no flood water, nothing comes in. So inside, this is a testing bed. In fact, we can test our own controllers. These are the controllers, charge controllers. Okay, this is a grid connected inverter. This is the distribution box. Everything is run, whatever, like lamp or AC, air condition inside, it will be run by the charge inside this 8 battery bank. Okay, so we have only 8 battery banks. So we have been using it. So there is a AC, air condition, and still we are trying to arrange with our, like, so-called tables, or like, you know, students, that 2 or 3 students can sit and work here. You know, we are trying to make it like that way. So when it was commissioned, it was supplied to us. So so this is the picture. If you ever come to Malaysia, to our university, I can take you there. So that is the thing. Now I come to conclusion. First of all, we have seen the photovoltaic systems are configurable according to the needs. Whatever needs we have, we really can cater as a standalone system, but it depends on your budget, definitely. There are 3 main kinds of standalone systems. Okay, like kinds of systems, like standalone system, grid connected system, and hybrid systems for small scale PV systems. Then standalone sizing has versatility in the application that needs energy storage. Yes, definitely in standalone systems, we cannot, because we need energy storage, because we have to use it at night. At night, there's no sunlight. So we have to think of energy storage, like batteries, supercapacitors, all those things, but usually batteries, large scale batteries. And number 4 is, I have shown the example chronologically, that the design concept. Okay, first of all, and I have shown analogously, like, for example, if you want to collect the rainwater to make it drinkable. So similar kind of analogy I have used just to make you understand. Okay, with that, I'd like to conclude my talk, and now it's open for question.
Thank you so much, Prof, for your wonderful and effective session. I really appreciate, and I also surprised, like I have seen many things new for me. Like we are working on solar cell, how to increase the efficiency. So behind the scene, actually, big room of thinking that why even we improve the efficiency, why we can't get the enough support, because of we can see that now we have 20, but actually due to this region we just maybe receive only 10% or 12 the proper utilization.
Yes.
The photovoltaic system. I can compare with I love your when you use the example of water, how we filterize the water and how we drink, and also it seems like a proper groundwater. Like previously, our like previous generation, they were not aware about the ground utilization of groundwater, so they just use it like everywhere. Now we are facing the groundwater problem. At the same time, I can say that the solar cell efficiency, even we increase 80% or 60%, if we are not able to find out this problem, so we'll not get actually the enough energy.
Real benefit. Real
Yeah.
benefit, the real benefit of it. You have to understand that solar cells, or for example, particular kind of solar cell you made, but you are putting in a wrong place. Maybe the solar spectrum, even the spectrum does not match. You know, in Malaysia or in Singapore, or in Thailand, southern Thailand, solar spectrum is also different. It's not, because we are measuring the solar cell inside the lab, which is very, like, you know, standard condition. But whenever you are putting outside, you have to understand it doesn't match, may not match with the real outdoor power, okay, from sun. So we have to consider all those things. At
the same time, Prof, I learned new one thing, like battery life. Like when you say that normally when we use battery, our thinking like we'll use 100% and then we'll charge it again. But that's the problem of the lifetime of battery. If we can use properly, so we can save our resources, at the same time also money. It will be long life for battery. And yeah, and also mathematical, many things. I think huge research is still now we need to focus on that. And without that, actually, we need to connect with the, not only we should not think only just to how to increase efficiency. There are many things we need to focus on that.
Yes.
Even system loss. Even
yes.
we buy the like a converter, we don't know it's work or not. And we don't know they are supplying proper utility or not. We don't know anything. So we need the proper research on that. And then now I would like to invite, I think some of us the supercapacitor, and they want to know about that. Could you please?
Okay, I mentioned, in fact, let me share, let me stop share first, then let me share again, because I'm teaching the energy storage in our university. If I can open up that file, it says the energy storage has, just give me a second. So supercapacitors, just a little bit. Okay, I'm not sure. Okay, let me check whether you can see.
Or anyone has any question, please feel free to ask any question from audience. Okay,
if you can see my slide, energy storage system, okay? This is,
yes, we can see it.
Okay, there is, if I take you to the slide, this slide, you see, you know, the power-wise, this is the power, okay? How much power they can store, and this is the discharge time. Discharge time wise in second, it's ultra supercapacitors are very good. Like within a second they can discharge, but power wise, they're still in the range of 10 kilowatt up to like ultra supercapacitor, not like, others. Like they have like lithium ion batteries within minute they can do, and it's still like, it's super, they're good solutions, but still, I should say like, there are other options. So ultra supercapacitors or supercapacitors are good option, but still, and also it is expensive. The other thing is expensive, and that's why there's, I have also this characteristic parameters of different energy storage technology. For example, lead-acid battery self-discharge is low. Okay, if you compare with the, where is the supercapacitor? There's no supercapacitor here. So I can show this using this one. Like power density wise, still ultra supercapacitors are still in the low range. Okay, not the big range. Still, and also they're expensive. Lead-acid battery, nickel metal hydride batteries, or lithium-ion batteries, or even lead-acid batteries. They're still like, they are dominating the market. But ultra supercapacitor, maybe if the researchers come out and come up with more storage, more, it has a very good, like, within second discharge, it can discharge within second. But the problem is the container, like how big they can supply. So that is the, I think, still bottleneck. I think this problem will solve soon. Then maybe we can get more ultra supercapacitor as the storage for the PV systems. But still, I say we are now transiting. We are now moving away from lead-acid battery to lithium-based batteries in the solar PV systems. Okay.
Thank you, Prof. Any question from audience?
Okay.
Any question from audience?
Once again, I just make
Yes,
sure
Prof.
that okay, the solar system, like how we design a solar system, is, as I mentioned, is a science, because you have to calculate something, is also art. How you reach, how you design so that you can reach, you can maximize the output from it, so that your needs can be matched with your supply. So that is art. Okay, you choose components. As I mentioned, that is, solar panels are heart, charge controllers are brain, and batteries are stomach. So you need, your stomach should be full, otherwise you cannot work, right? So your brain should work and your heart should pump. So we need, although we always look into the solar panel, we try to give the blame on the solar panels, but there are also in the system, it's not the solar panel, there are other components that may not give you the expected output. You are buying the best solar panel in the world, but you are not sizing it, thinking of others, other components. So you may not get the best combination, best efficient output. So that is the thing.
At the same time, Prof, also like we need to know our demand. Like if our demand like 2 kilowatt, so maybe our battery should be more than that, battery backup. Then we can make a sustainable system.
Yeah.
Otherwise, it would be difficult to maintain the balance, and maybe our system will not sustain for a long time.
Exactly. Battery, like, if you make the battery, like the sizing is not, I said, like, you see the battery, there are out of 8 steps, I think 3 steps are for the battery. First step is to know how much energy you need. 3 steps is for the battery, then 2 steps for the solar panel, then other 1 and 2 is for controller and inverter. So 3 steps in the sizing is related to the battery bank. How you distribute the battery bank, okay, that's not just only one battery, you have several batteries. So you make a battery network so that you can sustain long. And the batteries, there is a recharge and discharge cycle. So if you discharge quickly, the battery will not last, the battery will not be sustainable, as you mentioned.
And Prof, in future, I think what you show the innovation of solar cabin, right? So we can use it for maybe in future for car charging, or maybe electric vehicle charging. We can utilize it for like a mobile station in different area. We can utilize it.
Exactly. This is the beginning. In fact, we call it living lab. The lab is we just started. I just sized. I just like required this is my idea that how to make a like independent lab outside in the ground. We are not connected, so we'll be utilizing our own whatever like size we have. Rooftop we have, we just put the solar panels. Then we'll utilize our facility to test our own components like charge controllers inside this solar cabin. And also our students, there will be data, in that particular space, location, how much we are really getting, so all those things, it will be giving us some sort of idea so that we can implement it, we can replicate it somewhere else.
And for Prof, I have seen that in your presentation you show about PV Sol. So they will calculate for us like.
Okay, I think I will talk about this in the next session. Because yes, I have already prepared that one. So this is for the standalone system. From the basic, okay, just know from the basic, but you can use softwares. Now this software, just put, okay, this is this, then they will calculate for you. But in my next slide, in my next lecture, I will show you how, what is the gap between their calculation and my reality, because I have put solar panel on my rooftop now. I'm getting last 3 months, I got some of the data. I will show you grid connected one. So how those online softwares are not realistic, in fact. So there's a gap. So in my next talk, after lunch, I'll share that things that those softwares are just for like some reference, not as the realistic one. Because realistically, if you want to really size it, you will know that there is a gap, huge gap, almost 25% gap.
Yeah, Prof. And also like last time I heard one word like DFT, because previously I had no experience about that. And when I heard you post on the group that learning DFT, and later on I tried to do some study, and recently I've seen that you are talking about quantum espresso. So now I'm learning on that. I believe, but it's still difficult. But it's a huge knowledge actually we need.
You're always welcome. You're always welcome, because we are not that far. I think your students and your other colleagues, and we can always have a small session. We can discuss about the things, what can we do to boost our research collaboration. Okay, I always encourage this kind of activity. We can have periodic, like sessions, like knowledge sharing sessions. Anyway, I just saw that one of the comments here that thank you for the wonderful presentation, sir. I love how you explain and be precise about particular things. Sorry, sir, this time I could hardly understand as my head is bombing. I don't know, like the atomic bomb. We are not in Ukraine or we are not in Russia, so don't worry about that. So I try to our job is to make it very simpler. Okay, that's why the analogy I used or example I used is rainwater harvesting. Rainwater is pouring, it's everywhere, but whatever we take through the filter papers, only we can drink. So you always put in that mind that sunlight is everywhere, but whatever sunlight we cultivate, whatever sunlight we collect through the solar panels can be usable for our appliances. So just think that way. Rest is all like calculation. You can use it. I can share the calculation algorithm. You just contact me. I'll give you the whole like the algorithm. Just it is to let you know that there is a calculation behind, there is an algorithm behind, there is a reason behind why we do this way. Now, in the later, after 2 o'clock, whenever my grid connected, that is a different way. I will show you in a different way, that one, okay? I think with that, let's conclude this session and we can have
Okay, thank you, Prof. So I think from our first session, we already have done all of question response. And also from audience we don't have any question for. So I think that we can go for break, and we'll back 1 p.m. in Bangkok time.
Okay, thank you.
Okay, thank you,
Mr. Sharia. Thank you, everyone.
Thank you.
Okay.
So thank you so much. Welcome back again. And now time our second session. So after our second session, based on PV system sizing and build a small scale. So Prof will show us some case study, and I believe all of you will enjoy. So Prof, please take your. Okay.
Thank you, Mr. Sharia. Once again, welcome back. I hope you got a good break. just one hour. Okay. Once again, I would like to just show the PV system sizing grid tie. Grid tie means wherever we have the grid, utility grid, we, in that case, how we have small scale system. I will give you some case study plus the design concept, all those things. Okay. Before I start, just let me give you a brief idea about what happened in last 10 years. Okay, last 10 years, like the data. Okay, the data that we got until 2021. So I mentioned today that one small cell is around 3 watt peak or 6 watt peak nowadays, and this how much PV capacity is installed all over the world. Okay. So this chart shows that data starting from 2021. In 2011, the total capacity of in 2011, the total capacity was around 70 gigawatt peak all over the world. Okay, we added 31 gigawatt peak. Of previous year was 40, so 70 gigawatt peak. Okay, and then every year there's cumulative like value, cumulative installation number. So we add every year 31 gigawatt peak, then 30, 38. So in this way, we just accumulated the value says that even during the COVID last 2 years, 2020, there was a 139 gigawatt peak extra installation happened. And then in last year, 2021, 175 gigawatt peak happened. So now the total value is 942 gigawatt peak. Okay, so this is the value. So hopefully soon we'll be reaching terawatt, hopefully. So what does it mean, in fact? This value, what does it mean? Okay, it says cumulative solar PV capacity of 942 gigawatt peak by 2021, which means nearly 942 nuclear power reactors. Okay, nuclear power based solar stations, power plants are also possible, right? So each nuclear power station is around 1 gigawatt peak. So if you say that way, so we can say that by putting 942 gigawatt peak with only solar, we have replaced, okay, we have replaced 942 counts of nuclear power stations. So this is one, it is a great achievement for humankind. In the last 10 years, up until 2021, we have we really helped the whole world. Okay, I mean, reducing the dependency of nuclear power station. We all know that the Fukushima nuclear power station disaster, or in Chernobyl nuclear power station disaster. So all those disasters, if we think this way, that solar power stations is no more small scale. It's no more just like, you know, a few lights, a few bulbs, a few appliances. It can really help in large scale in terms of energy generation. So please remember this value, 942. So please remember this value, that 942 gigawatt is the number until that solar power installations happened until last year, 2021. And it means that humankind has replaced 942 counts of nuclear power stations by simply solar power plants of this scale. So this is a good number. Now we say that nuclear scale power stations are also possible. Okay. So I would like to show you the next thing, that how the price, okay, for example, the price, electricity price from different sources, for example, biomass, geothermal, hydro, solar PV, concentrating solar power, offshore wind, onshore wind. There are two data of 2010 and 2017, 2010, 2017. If you look in the x-axis, you can see the price solar electricity from solar panel was almost 0.36 US dollar per kilowatt hour, but it dropped in 2017 up to 0.1 US dollar or 10 US cent, which is as same as others. If you see the others, our value is roughly around 0.1 or less than that in some cases. But it is quite like, nowadays the electricity generation, 1 kilowatt hour of electricity from solar PV is as same as other competitors. Even you compare with other so-called renewable energy resources, or if you compare with the conventional resources, so it is, we can call it neck and neck. And how it happened? Because the significant price drop happened in last 10 years. Okay, solar PV, the price dropped significantly in last 10 years. And recently, IEA, International Energy Agency, declared that electricity from solar PV is the cheapest around the world. So this, this declaration came in place in July 2020. So it is cheap. In fact, I mean, if you go anywhere, I have another data, but I didn't show today. So the electricity, 1 kilowatt hour of electricity from solar PV power plant is the cheapest among all the electricity producing generators. Okay, now, as I mentioned today, that I will be giving the next part is about the grid connected PV system. Of course, grid connected PV system, there are many grid connected systems, small scale and large scale. It is not possible to cover everything in 1 hour and so. So I'll be just today focusing on the grid connected PV system of rooftops, okay, small scale one, not like LSS, large scale solar farms. If time allows, maybe I can show 1 or 2 slides on that one because it's quite big. Okay, so today's outline is grid connected PV system, the configurations, the grid type PV sizing, how does it happen or how do you do with that, and NEM. There's a term called net energy metering. This is the contractual thing that we do with the utility, because if NEM is not active, or so it is not possible, in fact, that you can connect to the grid. You just cannot simply connect to the grid by your own. You must have a contractual thing with the utility. And finally, I'll conclude. Okay, once again, those who are attending this lecture. So this is about the PV, solar PV electricity generation system, grid connected. The solar electricity can be also integrated into an electric grid, utility grid system, because usually we know that we have poles, electric poles that supply us electric power to our home. So what we do, we just put solar panels on our rooftop, and of course, maybe first of all, there are priority that we have to use first. We have to consume the energy that we are producing, but we do not store it. We do not have any battery up here. What we do, it is whenever we are not using, whenever we are producing more than our usage, we just simply send it through the meter to the utility, and whenever we need it, we just buy it back, something like that. But of course, definitely there will be a contractual thing that how much benefit I will get from this selling and buying. Okay. The benefits: reduced electricity bill. I'll show you some of the results that I have got in my case. I have also put solar panels on my rooftop, so using that one, I will show you how much I am really being saved. So the second thing is increased value of residence. Third is positive environmental contribution. Of course, I will show you how we are positively contributing to the environment by putting solar panels on our rooftop. There are some calculation also. That means how much carbon dioxide reduction. Because every country has pledged by 2050 we want to be carbon neutral. Okay, that means the carbon dioxide, total number of carbon dioxide emission, and the sinking the carbon dioxide from the atmosphere. So there should be equal, so that we do not produce any more carbon dioxide to contribute in the global warming. It is irrespective of the countries. Thailand, Malaysia, every countries have pledged already in the COP26 or COP21. All those United Nations policy making gatherings we have already pledged. We have already said that we will reduce the carbon dioxide emission or become carbon neutral country by 2050. So I'll show you how even our, like this small rooftop system can contribute in the carbon neutrality. Okay, next is design consideration. In this case, unlike the small scale solar system, we have to calculate, like, how much we use each, because we have to be self-sufficient in that case, right? I mean, we should not feel any kind of lacking in electricity supply. That's why in small scale PV system, we want to be self-sufficient, not only for one day. Do you remember that we tried to have autonomy for 3 days or something like that? So we have to make more battery banks, all those things. So that was for the small scale. But in this case, you don't have to be self-sufficient because grid is already there. So the more you can give, the more to, the rooftop space that you have, you can put the best use of it. Okay, and then you just sell the electricity to the grid, and that is the thing, that how much budget you have. And again, now you don't have to pay from the beginning. Sometimes some of the solar installer, they are giving us some sort of partial payment, or some sort of segregated payment, you don't have to pay at once, you can pay by 36 months or 24 months. So the cost of this is an issue, but it is also now, because of the different policy, at least I can say for Malaysia, that now it becomes very affordable. Okay, I don't know how to remove this one. It is really okay. Grid connected system, as I mentioned before, there might be 3 different ways. Okay, first of all, grid connected system is, you look into this one, utility line. So you have PV array, grid inverter, meter. So what do, because everything has a scheme related, FIT, we call it fit-in tariff system. Whatever you sell, you can get money. Okay, you can get money you can just simply claim money from the utility. But in many countries, FIT system is no more active, because the government cannot pay you more anymore. In fact, that's why they now change to NEM or Selco, self-consumption first, something like that, NEM Selco. So this is the one that in companies like manufacturing plants, they have huge rooftop space. So what do you do? You put solar panel on your rooftop, you use your energy, and then you just get the extra energy needed that from the grid utility line. So that means the energy does not go to the grid in this case. This is one kind of system. It is under Selco. We call it Selco for large scale, manufacturing plants. They have huge rooftop space, so they can make use of it. But we'll compensate them. We'll give them the extra energy from utility. That is what the utility says. But for small scale, like rooftop systems, it is a bidirectional. You see, PV, grid inverter, so you can sell and you can buy back. So this is the system that I'm going to show today. Okay, this is no more inact. So that's why, although it was this isn't the same, these are same, but in this case, it is always export and you'll get money. But in this case, it's not the money. You will not get the money. You'll get some credit, and that credit you can use within 1 year. So there are some scheme change. They call it net energy metering. So the difference between FIT, feed-in tariff, means that means how much feed in you are feeding in to the utility, you will get the money for that. That is called feed-in tariff system. But NEM, net energy metering, is it is just keeping track of your so-called import and export. And finally, they will give you some credit, and that credit you can use within 1 year of time. Okay, so let's start. So in the grid connected system, the size, it is much less complicated than the off-grid system. As I mentioned, in off-grid system, you have to be self-sufficient. That means you do not rely on anyone else. You have to rely on yours. So you have to make the system very robust. You cannot fail, and it should be very, I should say, to the point. How much you need, it should be always ready. So it was very like that's why this so-called the algorithm was a little bit tedious in that case in off-grid system. But here it is more on client's budget. How much money you have, because you already have grid connected to your house, but you want to reduce the grid dependency, and you want to put you want to be like you want to get some, like you want to save money, in fact, from electricity bill. Electricity bill is ever increasing, but you do not have that much maybe that much money. So that's why this budget is one of the main key constraint on key consideration. Then available area, how much area do you have on your rooftop? Okay, you're living in an urban area, and maybe you do not have a rooftop area, or you are living in a villa, so you have more open space. Okay, and then annual energy production and consumption at the site. So you need to know how much you produce and how much you consume. Okay, and choice of materials, critical panels, inverters, etc. So this is pretty much simple. That your budget, your availability to put the solar panel. Okay. Okay. Then a grid tie system should be viewed as a supplement rather than replacement. You cannot replace the utility grid in your, because usually in urban area, we are pretty much like, using too much of energy. Honestly speaking, we have so many appliances, so many things. Okay, we use washing machine, we use heaters, water heaters, etc., which are really, really energy consuming appliances. So we cannot see a grid tie system. Maybe you can compensate 30% of your usage. You can compensate half of your total usage. You can compensate maybe 70% of your usage. It depends on how big user you are. So you cannot really replace your you cannot really have the self-sufficiency by this kind of system, because you have a limitation on your rooftop, on the available space, first of all. And you are living not in an urban area where we do not need that much, right? We do not need air conditioning. We do not need so-called a washing machine, for example. Okay. So grid, utility grid is always present and not necessary to fit the consumption load. Yes. Okay. If the load requires more power than the array can provide, utility can supply. Okay, so whatever the solar panels can supply, we will use it, or we will sell it to the grid, and rest we can get from the utility. Number 3, however, the PV system goes down with the grid failure, but revives back. But the PV system, okay, because of the safety, whenever there is a blackout in your locality due to the some of problem, so grid system also that time will fail. In fact, it is made in a way that it should stop. Okay, so that's why, because it is supplied to the grid, so grid cannot take, so we just stop sending to the grid. So it is the common design concept. Now, about the budget area. First of all, budget is always the primary constraint or concern. Your money, how much money do you have? Okay, how much, although you have a solar, you may have a certain 20 meters square of rooftop space, but can you really cover the whole rooftop with the solar panel? And do you have that much money to put the solar system? Okay, so this is the first constraint. Second, mounting area could be either roof of house or business, rarely ground or pole. Mounting area usually the rooftop, not the ground, because ground space is always very expensive in urban area, right? And there's no ground space available in the urban area, always rooftop available, right? So this is the second thing, the mounting area, always rooftop. So we have to put the solar panel system on the rooftop. Okay, so there is, of course, your system should be robust. Your system should be able to sustain the some certain natural calamity, all those things. So it should be robust, very robust. Okay. Then site survey is a must. You must survey the site. Okay, that for example, is there any shading? Is there, is this place covered certain period of time by cloud or by shade, means like long trees and other obstacles from other houses? Because we know that for solar panels, we definitely need direct sunlight. Even diffuse sunlight works, but direct sunlight is pretty much one that we need, in fact. So we have to survey the site. We must know using using our kind of surveying tools. Maybe it will take a few months time if we do not know. And sometimes we can use Google Earth mapping, Google mapping, all those things. Okay. Total area should be known to know modules power density of the or the number of the watt peak per square area to choose well-matched panel supplies. So we have to know the total area where we can put the, even we have full area rooftop, but we cannot put the full area of the rooftop because sometimes we have to put some margin for some other reasons, for safety reasons, for fire. Someone has to walk, or there's a, for example, there's a roof leakage. So someone has to go up and then fix the leakage if you have a tiles. Okay. But it is recommended to consider dead spaces for maintenance apart from local jurisdictions. Okay, there's some local law that says no, you cannot put 100% cover. You have to put some certain space just for safety purposes, so that firefighters can walk on rooftop, or even in case of your rooftop, some leakage, you can go. Your other contractors can go and fix the roof. So there is always a dead space. You cannot simply cover the whole space. You will see some of those in my slides. Then number 3, in the site survey, the size of the PV array will change as string configuration requirements, like string, how we connect in series, in parallel. So the PV size may change. Nowadays, PV panels are quite big. Each panel is more than 2 meters high, even higher than a single person. Okay, it was very small in the beginning, but nowadays, 2 meters by 50 centimeter width. So we need cranes to put on the rooftop. And the size, according to the, for example, I need 5 kilowatt system. So how many panels should I put? Should I put 11 panel or should I put 10 panel? So all those things are coming together. So these things we have to consider. So some of the pictures here I have shown. Okay, first of all, this is the one of the typical rooftop system. So is it on the tiles? We are putting solar panels, but we didn't put until the end, right? So we have some space on the top, around it, and bottom. So we can walk around, we can check, we can unmount anything, we can go, even we can walk on the roof. It's so robust that we can walk. It is called pole mounted. It is very unlikely because we have a space constraint. So mostly in USA, in northern part of the USA, they have less sunshine, so they put on the pole, and it is it's a tracked one. It can track the sunlight. So it is different kind of solar cell. It is not the similar kind of solar cell. It may be gallium arsenide-based high efficiency solar cell with some concentrator, with some lens on top. So this is also possible, but we need so-called tracking system. You see, the shading means this shade is coming here, but sometimes if you put very nearby, so this one will shade the other panel, right? This system. So that is one. That's why we have to keep space between the two in pole mounted systems. This is called ground mounted system. Yes, this is mostly now in large scale solar farm, 50 megawatt, 60 megawatt, 500 megawatt. We can see around the world now these big solar panels. Okay, so in mega or in gigawatt range also we see this kind of ground mounted, but usually we use barren lands. We do not use cultivable lands because land is also issue in some countries. Okay, and then this is the premise, not our house, but maybe school, maybe some office. So we have huge rooftop space, so we can put solar panels just to compensate part of the electricity consumption of the building. Maybe it's a manufacturing plant, maybe it's something hospital. Okay, so this is also very popular in many countries nowadays because they have rooftop space and rooftop is not being used for any other reasons. Okay, so we can put solar panels. Okay. Also, the LSS, we call it, this is the abbreviated word of large scale solar farm, large scale solar PV systems, like this big. This is near, this is in Malaysia, around 78 megawatt peak. Okay, 78 is quite huge. Okay, there are also 50 megawatt peak. There are also smaller one. Okay, this is the one that we call it LSS. These are all power plant. Like nobody was using this land, so suddenly we have a power plant, and it doesn't produce any toxic gas while it is producing the power. Usually power plants, they produce huge amount of toxic gas, right? So this is one of the advantage of this kind of power plants. So we can select unused lands, barren lands. Okay, somebody may say, oh, okay, you have destroyed the so-called this kind of forest or this kind of bush, and then you put the solar panels. How to compensate this green land? So we say that no, beneath it we can also cultivate, beneath the solar panels. So somebody grows grass or some other even potato. There are some examples of that. Okay. Okay. Let me start because this shows that different kind of policy, because grid connected means the government or the grid owner is sometimes semi-government entity. In Malaysia, it's called government linked company. Okay, like Tenaga Nasional Berhad or National Energy Supplying Company. So that company, definitely they own the power plants and they own the network, the power supply network. Okay, and that's why we have to have, whenever I have rooftop solar or I have a solar system, to connect to the grid, definitely I have to make a contract. Okay, long-term contract, like 25 years or something like that. Usually solar panels last for, they say 25 years or more. Okay, so we have to have a contract, like 20 years, 21 years sometimes. So we have to have a contract with the utility company. Okay, so I'm just showing the kind of policies existing in Malaysia. For example, for solar photovoltaic, biomass, small hydro, these are all renewable energy sources. For solar, we have 3 policies available. Selco, self-consumption. First of all, you consume self, and rest will be provided by the grid. So this is usually for the small-scale manufacturing plant. Or so this is one of the government agency, like Energy Commission is taking care of these contractual things. NEM, Net Energy Meeting, is another government agency is taking care, or we have to make the contract with them. Okay, so NEM says, okay, you can put solar panel on your rooftop, you can connect to the grid, but okay, we will not give you the money. Okay, we will not give you the money for the energy you are generating, but rather, it's like compensating, because the energy price goes higher if you use more. So we'll compensate, we'll deduct those higher slab, the energy price by how much you produced. So it is a very good system. In fact, the contract is very nice, and NEM now in Malaysia is NEM 3.0 is in active. So I will show you how it goes on and how I'm benefiting, in fact. And then there is another system called large scale solar, but you have to bid. You have to bid and you have to make a contract for 21 years. Okay, you have to bid for 50 megawatt, 100 megawatt, something like that. So it's not for our, in fact, not for us. It's large scale solar. So what we are like concerning today is about this one, that small grid tie solar system with NEM, okay, net energy metering, okay, contract. But there's also feed-in tariff, but no more after 2017. I think there's no more feed-in tariff in Malaysia. Only for biomass, they are still allowing feed-in tariff. That means biomass still is a little bit expensive because you have to have biomass, in fact, from somewhere else. If you do not have the biomass, so you cannot really produce electricity. So in this case, SEDA is also Sustainable Energy Development Authority is taking care of this FIT system, feed-in tariff system, but it is no more for solar, it's still for biomass. Okay, mode of purchase. How can you purchase the system? Either you can buy cash, bank loan, even credit card. Yeah, we have been last 2 years. I think NEM started from 2021, January or February. So the quota of 300 megawatt peak is already finished. They gave another quota. So people are being encouraged to put, like, by credit card, you can pay for your solar system on your rooftop. And this credit card do not charge the whole thing at once. They will monthly charge you equivalent to your maybe bill, equivalent to bill. So you'll see that like load on you is really, really not that much. You will not feel any pressure, even though you're putting solar panels. You have purchased solar panel system. Okay. Now, let me take you to the journey for this one. I don't know how to remove. Can I really remove this one? No. Oh, okay. I have finally, it is possible to remove that one. Okay, estimating site's annual energy production. First of all, this is the design concept, okay? If space is known, if you know where you're going to put the solar panel system, for example, I'm sitting in a premise now, so on my rooftop I'll put, so I can really estimate the annual energy generation, how much sunlight I'm getting first, okay? So first of all, my input is sunlight energy, so how much I get first. Then also I have to check what kind of agreement is available in this place. Is it FIT? Is it NEM? Is it CELCO? There are 3 different policies are in Malaysia right now. As I mentioned that for solar, it is NEM and CELCO. So you have to check. If you are not entitled for this kind of contract agreement, then even though you size it, you cannot really implement it, in fact. Okay. Next is estimation of solar energy production. Okay, how to do it? There are some software. Okay, PV Sol, PV Syst. These are the software. If you click it, in fact, you can download, you can play with it, because they will not show the algorithm. They just show you the solution. If you put certain inputs, then you'll get the output, how much you can understand how much solar energy can be harvested in a year, and how much per month, and how much will be the cost. So they have already created those kind of software using the algorithms that we used before. Okay. And making a software is just simple. That if you know the algorithm, how to where is the conversion? Is it 1-to-1? Peak sun hour. That peak sun hour times, we just multiply peak sun hour with the IMP. So that is the case. It is like how much peak sun hour we are getting, and we just multiply with the IMP of each panel. So that much ampere hour we can really harvest. So that is the key point. It is that much 1-to-1 ratio. Okay, I'm just asking you to recall the system design in standalone system. That thing is peak sun hour. How much peak sun hour you have in your locality, and you just multiply the output power of output current IMP, then you will understand how much ampere hour you can get in a day. So it's pretty much same for this one, but they will not show you. And also there are for larger commercial systems, you can use PV Sol and PV Syst. PV Syst, you have to download a program. For a small scale residential things, you can use PV Syst, and also you can use PV Watts. Okay, there is a software. I'm not sure whether it will work today. Okay, for example, if I click it, it should show some. I think. Oh, you don't see it, huh? I think I have to share the whole screen. Okay, let me reshare. Let me stop share. Let me reshare my whole screen. Okay. Okay, if you see these are the software you can download. I think PV Syst you have to pay, For this one, you don't have to pay. This is for residential and small commercial systems. The best way is to use the PV Watts. So you can put, for example, if you click it, I have to click it this way. Okay. Mr. Shari, can you see?
Yes, Prof, we can see.
Okay. So if you just simply click that, then it is National Renewable Energy Laboratory of the US. They are giving you the tools, how to make it near data set, you can do in that. But I'm going to show using the screenshots. Okay, I have already prepared the screenshots, so I'll show you. So you can go there and you can put your input value. Where are you located? How big is your space? Okay, which way your house is facing? So you have to give some basic information. For example, what the amount of energy the design PV array can produce in kilowatt. Okay, the tilt, orientation, and shading effects of the array, because your rooftop is already tilted, right? I'm not sure in your country how much tilting you're using. In Malaysia, we use 20-degree tilting, so we cannot change the tilting anymore. Okay. And also the software will create a total solar resource factor for a site. Okay, that means how much we are getting in a day, how much we are getting in a week, or how much getting in a month, or how much getting in a year. So we can get all those information by taking into account of some of the data. Estimation in kilowatt hour can be monthly or yearly, as well as cost of the energy can be found from this. Okay, PV Watts finally provides a report. Also, finally, they will show you a report that estimates monthly and yearly energy in kilowatt hour. I mean, your system produces. First of all, you'll give that I have this much space, free space. So they will calculate, okay, where are you located? How much solar resource coming from the sun in your area, okay? So that after that, any estimation is just the estimation, but here the estimation is just the estimation, as the energy production may be affected by the installation methods. Because you're not using the maybe you are not using the good panels, maybe you're not using the good inverter. So this, whatever they are showing, it's just a standard value. It is not the realistic value. Okay, that's what I'll tell you that why my realistic value, because I also did a study on this. Okay, I have done 1 year of study on my rooftop. I want to put solar panel on my rooftop. I want to be I want to contribute to the carbon neutrality to the extent that I can do. So that's why I studied different vendors. I talked to them. Can you put solar panels? How big the solar panel will be in my rooftop? And how much money do you have to pay? And can I pay in installments? Can I pay in 3 years of time? Can I pay monthly? Okay, monthly only 500 ringgit. I want to pay. I cannot pay more than that because my bill is around 500 ringgit or around more than that. So I'll just pay the bill, and I want to be the owner of the solar system on my rooftop. So there are so many that kind of thing in this case, not the sizing, because you're already constrained by the size of your rooftop. Your roof is already limited. You cannot put more than the rooftop, and of course you have to put some extra space, dead space. Okay, there's no average size PV system to fit all of our electrical lifestyle. Fit to all, as our electrical lifestyle varies, because my neighbor and our house have completely different lifestyle. Our bills are always over 500 Malaysian ringgit or 100 US dollar. Okay, which is in the higher end side, because I have a big family. We are 6 persons in the house, and during the COVID we didn't go out, so we are all staying in the home. So every month we had to pay 600, 700 sometimes ringgit Malaysian currency. Okay, 700 ringgit Malaysia per month. Okay, but okay, that's why I was thinking how to compensate, how to just reduce the bill. And I want to show that I'm also a promoter of renewable energy resource, because I'm teaching it. Okay. Okay. You can also check this. You can also check this website. You can go in, but I'll show you now how to use this calculator. Okay. This is, we call it online calculator. You do not have to download this one. PVSys, PVSol, you have to download. You have to put the value. After downloading the program, you put the values as input parameter. In this case, this PV watt, this is a simple like an online, we call it online calculator. The calculator you also can make if you follow my algorithm algorithm that I showed in the small scale standalone system. Okay, first of all, if you go, you just put the PV watts PHP. I think I have down this screenshots is not the recent one, is previous one. So first of all, you put the solar resource data. Solar resource data here, this is international Kuala Lumpur data, but Kuala Lumpur is 23 or 25 kilometers away from our place. We are living near Putrajaya, the capital, like administrative capital of Malaysia. But the data is of Kuala Lumpur. First of all, I'm not getting the 100% matching data, the weather data. So this is one of the mismatch, okay? Because the resource data is available for Kuala Lumpur. Maybe the meteorological department is in Kuala Lumpur and they are uploading the solar resource data, solar irradiation data, solar insolation data, okay, of Kuala Lumpur, not of Putrajaya. Because in Putrajaya there is no weather station, okay? So first of all, the mismatch may happen because our Putrajaya and Kuala Lumpur, they have completely different weather patterns. When it showers in Kuala Lumpur, it doesn't shower in Putrajaya. Only roughly 25 kilometers away. It is very common here. You know, you see it is even 5 kilometers away, there is different weather patterns. So first of all, it may not give you the perfect weather matching data. Okay, so your input data may not be matching anyway, but you can use it. Okay, I have used, for example, in my case, this is I'm showing you taking an example of my rooftop. Okay, I have a certain amount of rooftop, so how I can put a rooftop solar, grid connected solar using this one. So first of all, I put that Kuala Lumpur nearest value. Then DC system size 5 kilowatt. What I put, because in NEM they said you cannot put more than 4 kilowatt. You can put 10 kilowatt system, but you cannot give us more than 4 kilowatt. My supply pipe to the grid is restricted by 4 kilowatt. So even though I make it bigger, really does not help me, okay, in sending the energy at any instant more than 4 kilowatt hour, okay, or 4 kilowatt second. But why I put 5? Because I want to make sure that I want to cover all the losses. Okay, I can send 4 kilowatt hour, but I put 5, means 20% loss I'm encountering and putting in my mind. So this is a good system in that sense. So what I did, I said, no, I do not want to put 4, although it says the government is willing to take only 4. So I put 20% extra because I know that there will be several losses. Okay, and every information is I means information. What is DC system means? The total kilowatt peak of the solar panels. Okay, 5 kilowatt peak means there are 10 500 watt peak panels. Okay? 10 500 watt panels or 11 450 watt peak panels. Okay, something like that. So it is that way. But how many panels? 5 kilowatt means if I keep a smaller panel, that means I have to increase the number of panels. And module type, it's called like standard module, not like high efficiency, blah blah blah. Just normal standard, it's the usual one, not the substandard one. Array type fixed. It is not moving with the so-called tracking system. So it is fixed. Okay, open rack. Okay, on the mounting system on the rooftop. So see, I put system losses 14%. I said I was cautious. I put 20, but in reality they said, this software says almost 14% will be lost. If you put 5, 14% of that will be lost. You can calculate how much we can send. But again, I think I'm over cautious about that. So I put this tilt angle in Malaysia is 20 degrees because usually the rooftops are like tally tiles rooftop are usually so-called 20 degree. Okay, and azimuth is because south facing. Degree 180 means it is south facing. We want to put in the south facing roof. Okay, and it's for residential rate. We can put how much we are buying so we can understand the economic value of it. Okay, later on. Okay, next, what are the losses? That 14% losses. Okay, that you saw here, right? 14% losses. So if you click it, loss calculator. If you click it, you can come to know that there are percentage. This 2% loss in soiling because sometimes on this solar panel, sometimes there will be some kind of layer of soil or dust. Okay, which becomes a little bit sticky unless there is a huge rain. Okay, unless the rain cleans it. Luckily we are not in some places. It could be 5% soiling loss. But in Malaysia, almost every day we have rain, so we consider like 1% or 2%. Shading, there's no shading loss. Although I put 3%. Shading means it is because of the cloud, all those things. Snow, in Malaysia, there is no snow. Mismatch 2% in the cabling mismatch, wiring mismatch 2%, connections, there's 0.5. Everything has information. Huh? If you click the information, everything will be more, they'll give you more details about this kind of loss. Aging, no aging factor because we have the new one. Availability 3, 3% loss in availability. Sometimes it's not available. Everything will be explained further. Okay. Then, okay, 14% loss to 20-degree tilt, azimuth 80, 180 degree. So, sorry. Okay, DC to AC ratio. Okay, 1.2. That means 120%, right? So AC is 100. So I give 1.2 of DC. That means 500. I gave 5 kilowatt, but I gave extra, in fact. You know, my output size is 4 kilowatt. They said, government says you cannot send more than 4 kilowatt. So I put 5 kilowatt. That means 8. You know, I give oversized it. So the ratio is 1.2 or 1.25. Let's say, right? Let's say 1.2. After the inverter efficiency is 96%. Nowadays, inverters are quite good. Ground coverage ratio, there is no ground coverage because it is on rooftop. Okay, it's 0.4. So these things are and everything has more details. Like if you click the information, everything will give you more like an explanation about this more. Okay, what are the options, all those things. Okay, this is the locality that we are living. In fact, you know, this is the house. It's a typical house, like, you know, as linked house, we say. In our case, I have a small, you can see this one as, I have something else. In fact, on the back side, on the north facing roof, I have a solar thermal water heater. When I came into this, you know, this neighborhood, so I put a solar thermal water heating system to supply hot water to all the bathrooms or all the sink, so that I can use natural hot water. I don't have to use, you know, shower. In early morning shower, maybe the water is not hot. So usually, so this is the hot water system. It is running for the last almost 8 years. Quite good. Still the quality is quite good. The water is really hot. So it is not solar thermal system, it is solar hot water system. I think you have seen it. So I have only space on that means I have only space on the south facing roof. This is the borderline. This is north facing roof. This is south facing roof. Okay. So I have only this much space. So I have to put how much space I have. So how much we can put. Again, I put those values, and I put some in dollar. I put that usually it's 1.24 US dollar. That means around 52 Malaysian cent, 0.52 Malaysian ringgit or something like that. So I just put the value. Okay, so it gives me, after that, when I ran the program, so it gives me monthly data. It says, okay, solar radiation in January 4.4, you can get 5.16. February, solar radiation, although big, but you will get 480 kilowatt hour. I don't know how they calculate, because maybe something is there. Solar radiation is quite good, like over 4, in fact. Solar radiation wise, over 4. I mean, it's quite good, but input wise, I see that some month 516, 480, 524, 474, 447 kilowatt hour. Huh? This is the energy produced. Okay, how much I saved in US dollar. So my question is, okay, so average solar is this, and average input solar is 4.1 kilowatt hour per meter square per day. Okay, this is roughly, I say it is correct, but usually 4. In our case, it is 4. And here I see that there's a big difference, because I put in July. You remember the value, July 448, August 472, September 478, but it is completely different. In my case, it was higher than this value. I'll show you later on. Just remember this value, 448, 472, 470, like roughly 450 to 470. This value, just 3 months, July, August, September. So the data, you can download the whole report, okay, yeah, for a 5 kilowatt system on your rooftop. Okay, so it will give you the total everything. So how much you can see. Same also, it will take you to some of the company that will sell the solar panel system. Okay, Plus Solar System. This is one of the company that my student has started, in fact, in almost how many years ago? 15 years ago. So Plus Solar is one of the company. Then other company that solar. So this will take you to the solar installation company's website. Okay, so what I'm going to show is that the total report says that total annual per day solar irradiation is 4.15, And in a year, it can produce 571 or 5.7 megawatt hour, okay? 5.7 megawatt hour or 5,716 megawatt hour, and which is equivalent to $711 in a year. So usually we pay, I should say, we pay $4,000 for this system. So now you see 4,000 divided by this 7. Let's say 700. If you pay say $4,000 for the system, so you will ROI, return on investment, will be how much? How many years? 4,000 divided by 700 means around what? Can you say, someone? Okay, 4,000 divided by 700. So roughly you will get 6 years. Okay, 6 years of time. In 6 years, you can get your money back, return on investment. That is true. In fact, it is true that within 6 years you can get your money back if you did. This is very, I should say, this is very kind of like reserve kind of calculation. In my case, I'm getting more than that. Maybe it will be 5 to 6 years. In between 5 to 6 years will be the return on investment. But the beauty of it is, like, after 6 years, it will run for another 15 years. It is good for 21 years, 25 years. Some of the solar systems are running for 25 years. Still, it is not degraded that much, although there is an annual degradation of 0.8%, but still it's running. So that is the beauty, and also other beauties are there. I will show you one after another. So the block diagram, now let me show you the block diagram, how we connect. It's very simple. Only we need solar panels and a grid connected inverter and one junction box. Okay, circuit breaker box or circuit box. Okay, you put all the solar panels either in some configuration, in array, in string, or in parallel way. So, and there will be a grid connected inverter, and then the grid connected inverter, through the thing, it will be connected to the electric meter. So always what it does not, this electricity will never be consumed by your home. It will be always sent to the electricity grid. So in Selco, you have to use it in fact. But NEM, in NEM contract, whatever you are getting, you will simply send the electricity to the national grid or utility grid. Okay, so they are allowing, so there will be no self-consumption here, just always sending. But of course, definitely you are using their electricity, and then you will have a these how much you send and how much you use. So they will take a total sum of it and they will calculate it, and finally you have to pay for the how much you consumed. So you'll save a lot, in fact, because you are reducing the high priced slab of the electricity. Because we know in Malaysia, the first 200 unit is cheaper. The next 100 units is going up. Next 200 unit is going more. It becomes double per unit price. So there is huge, huge cost difference between the first 100 unit and the subsequent units. Okay, so I'm just showing two block diagrams, how complicated they are, but honestly speaking, it's not that complicated. It's just that that you have to connect to a smart meter. Nowadays we are changing to smart meters. So a smart meter is very simple, that you just connect to the smart meter. They will give you that reading here also. It is not the conventional meters. I'm going to show.
Do we go for a short break?
Okay, no problem. Let's have a short break for 10 minutes. Okay, thank you.
So will you back? Will you back around 2:05?
Yes.
Sorry, 2.
No problem. Okay, thank you.
Thank you. Welcome back again. Prof, you can
Okay,
proceed.
thank you. So as I mentioned, that the grid connected system is, I mean, as a consumer, I mean, I'm a consumer, so I don't need to worry about that much. Whenever I contract even the installer, we call it installer. There are many registered installer in Malaysia, so they will also give you the best, like, solution. They'll come with you and you can check. Okay, you can check, you can compare the price. You just contact the installer, say, okay, I want to put solar panel on my rooftop. So how much is your proposal? How much it cost? Then they will come and they will give you the estimation. So that estimation may, of course, that depends on your rooftop space. If I say that I want to put five, I just contacted 5 different vendors before 1 year. I already studied through this, I know that how much and which one is good, but I know the solar panels, I don't want to go for the solar panels, which is not standard one. So those knowledge is needed, of course. But whenever I contacted 5 different vendors, then whenever they gave the price or quotations, then I found that there are difference. Definitely, there are difference, and roughly there are difference of $500 sometimes. I said like $4,000 US dollar is roughly the price here, but sometimes it becomes 5,000. Sometimes it becomes 4,500. So it is up to you now. Then I check with them what kind of solar panels, which manufacturer solar panels will be giving, and what kind of inverters you'll be giving, and what is the maintenance, how many times you'll come and maintain for free. So all those small things I compared with each of the vendors, and finally I decided to go with one. Okay, now let me show. So single phase, because our home are usually single phase. So how to connect? In fact, long before I did some study. Okay, so I went to some of the those who put long before, almost 10 years ago, they put grid connected system, which was not that time common in Malaysia. So how did they connect? For example, they have their main DB, MCB, main circuit board. So how they connect with the GCPV, the grid connected PV system. So they connect to one of the neutral link and then connect with one of the circuit breaker. Okay, so the connections are all known. So this is the 3 kilowatt peak grid connected system. 3 kilowatt peak. Every panels are small. Like in each string, there are 5 panels, and there are 4 in parallel, 5 in series, 4 in parallel. So it comes. Each one comes with 1 fuse, and there's combiner box. Okay, combiner box, and then we have the inverter. From the inverter, AC combiner box, and then PV meter. We connect to the meter, and then from the meter it is connected to the grid. Okay, so these are the how they connected, and these are the pictures that in one of our training institute in Malaysia, they show these to teach you how to do the grid connected system, because they are the trainer of the installers. So you have to, for example, you have this kind of rooftop, so you have to use this kind of connectors. If your rooftop, usually most of the Malaysian houses are having this kind of rooftop. So how to connect, how to do, everything is shown in this training center. So you can become after training of 1 month or 2 months or something like that, you can be a registered grid connected installer. Okay. So before the NEM 3.0, which came last year, I was trying to understand. So if I want to connect my whole rooftop, because I have a problem in the north-facing roof, I have a solar hot water system. So if I can cover the whole area, how much I can connect? How much will be the total PV capacity? I found that PV capacity will become 6.75 kilowatt peak. That time it was expensive. It was a little bit expensive, like almost 33,000 ringgit, which is around 8,000 US dollar in during that time, 2017, 17 to 18. That time NEM 2.0 was enact, but it was not. I mean, there was no restriction of grid connectivity. They will allow any kind of like PV system to connect. But later on, I found that no, we can connect only 5 kilowatt peak system or 4 kilowatt inverter. So we have studied this one. I studied this one, but I found that this is not lucrative. It will take almost 7 to 8 years, or more than that, in fact, 10 years of time, because this much money is quite expensive, 33,000 US dollar, 33,000 Malaysian ringgit. Okay, and also that's why I was waiting, and at that time I also learned how to do like connection, everything, like these solar panels, how they will be connected to the grid connect inverter, how they will be connected to the switchboard, and then meter. So there are some like, and also smart monitoring system. We can check through our computer, okay, through some logging into some site, and also maybe using some like app or something. Okay. So it was quite lucrative, but the price was high. In fact, that's why. And that time we have to pay. There's no credit card payment system. Okay, 33,000 ringgit you have to pay at once. Okay, which is like this is 33. I mentioned, right, 33,000 ringgit. Okay, 33,000 ringgit. This total investment is that you have to pay upfront. They will not allow partial payment, or they will not allow installments. So I could not go with that direction. Then whenever in 2021, the new NEM policy was enacted, and they now included like flexible payment. For example, you can pay whatever the price is, okay, just by credit card, and the credit card will bill you every month. Every month. Like if you want to pay like in 36 installments, it is possible. If you want to pay in 24 installments, that's also possible. So this NEM 3.0 is a little bit upgraded one, and that helps the consumers more than ever, I should say, more than ever. And the price, in the meantime, the price of the solar system has also gone down 20%. It was, I mean, again, it will go up, in fact. I mean, the overall scenario says that everything will be, there will be inflation soon in every sector. As you see that prices of our daily commodities are increasing every day. Not sure whether in Thailand is the same case, but in Malaysia, in other Western countries, we see that the price, maybe due to the COVID or due to the war in Russia and Ukraine. So, but when I contacted this vendor, one of the vendors in last year, then the price was quite okay, affordable. Like I should say 4,000 US dollar or 20,000 Malaysian ringgit that time. And I can pay in 36 installments. Okay, there is no upfront, like no burden of like huge upfront thing. And also they showed me some sort of like that the ROI will be 6 years. That means within 6 years I can get my money back, and I can really enjoy free electricity after that. Okay, so that is, I know, because some of the things, because I have been working on solar since 1996. While I was studying in Japan, I started like I was making solar cells in 1996, so small scale solar cells for my research purpose. And then later on, I learned the systems, everything. So I know that to some extent, of course, among the volatility of the world market, so this is the time to purchase solar system. So my intuition forced me, in fact, to go for it. And this year in June, they have installed and they have commissioned in July, 4th of July. So since 4th of July, I have some record I will show with you. Before I go into that details, let me share the policy. There are, in NEM 3.0 policy, the government has implemented one for domestic, like, this is for us, this is for government building, this is for commercial and industries. Okay, they have total allocated 100 megawatt. That means this is the quota. If quota is full, you cannot put any more. Mechanism rollover 1-to-1. That means in whatever the price I'm buying, I'm selling the same price. There's 1-to-1. Okay, opening date. So 1st of February it is opened. This quota opening date was 1st of February last year, and only for 3 years. Okay, they are offering if whatever comes first. If the quota is full before 3 years, then there will be no more. Even though you apply, you cannot get it. offset, then 10 years. Offset period means 10 years. Then later on, you have to connect with the battery system. So this is their own policy. We have nothing to do. And capacity is single phase, 4 kilowatt. I have in our house single phase. That's why I cannot go with the 10 kilowatt. Okay. And also I do not have that much space, rooftop space, that I can put 10 kilowatt, because 4 kilowatt is enough. 4 to 5 or 6 kilowatt was enough. Anyway, I went with the 5 kilowatt system, in fact. But this 4 kilowatt means it is the output. The inverter output is 4 kilowatt. Even though whatever kilowatt you put as a solar panel, the inverter will send only 4 kilowatt hour per hour. Okay. If my house was 3-phase, then my inverter capacity will be 10 kilowatt, but it's not possible. In our house, a single phase. So so we have to. I applied for this 4 kilowatt. Okay, domestic account holder. Anyone who has an account, TMB account, okay, can apply for this one. But these things, who will do? In fact, the installer will do for you. You call the installer whenever you like the installer. If the price is okay, if they commit that no, they will be giving you the good panels, good inverter, everything is good, and the price is okay. Okay, they can do it in a very short period of time. So whenever you are okay with those conditions, then you call them. They will do for you everything. I mean, it was just a very simple one. I didn't have to go anywhere. I mean, they came to our home and they started filling the forms, and they took the drone picture of my rooftop few times and design where to hack the wall. Should they hack the wall or no? I said, no, do not hack the wall, put it outside, all the inverters outside. Okay, there were so many, like, fine matching. So just to show, the 4 kilowatt system, they said roughly to 20,000 ringgit, but I put all the 4 kilowatt AC, but I put 5 kilowatt DC. This is 5 kilowatt DC. So I in fact gained at least 500 watt peak, one more panel in this price range. So that was the deal with that company. I put 5 kilowatt DC. This is DC side. This is the DC side. AC side is this. 4 kilowatt AC, 6 kilowatt AC, 7 kilowatt AC, 8 kilowatt AC, 10 kilowatt AC. So this is AC means the output. That means you can sell at any point 4 kilowatt hour second, 4 kilowatt second, 6 kilowatt second in any second. You cannot put more than 4. So these are the cap of your export. Okay. Anyway, since I put 5 kilowatt peak in the DC side and within this price, so I thought I'm the gainer here, because I negotiated. So finally, with one of the company, or many companies came, in fact. So one of the company, they showed that 4.5 kilowatt with 4 kilowatt AC inverter, I can produce 5749 kilowatt hours. And how much carbon dioxide I can reduce. This is the things, how much tree I grew within 1 year, or how much energy I can produce in a month. 473, in fact, more than that, more than 500. In fact, that's the thing I saw. I'll show you later. Is around 473, saving in 1 month for 244. In fact, not 300, more than that. Saving in 1 year to almost 3,000. Okay, saving in 25 years, because this solar system may last for 25 years. You can save 65,000 ringgit, and equivalent to carbon dioxide reduction, 4.1 metric ton of carbon dioxide avoidance per year. Okay, how many passenger cars driven by car per year? This much passenger cars, equivalent to this much passenger cars you reduce. Tree seedlings, how much tree you grew. So these are the things that is very nice. Like, you feel accomplished. You feel I am really contributing. Although I'm a small person, but I can really put in solar panel, even at the lower cost. I can really help by decarbonizing, the world or my neighborhood at least. Okay, so this figure is for central Kuala Lumpur. That means we have a little less from northern part, because northern part, near your Prince of Songkla University, I think you're getting more sunlight, which is equivalent to 1,350 kilowatt hour per kilowatt peak per year, but we are getting 1,200, a little less. So this figure is a little bit lower, in fact. So, this was the offer, but what I did, I just said, no, I want to put 5 kilowatt. So what they did, they put 5 kilowatt DC system. So at first, this is our rooftop. Okay, this is the rooftop. We have a solar thermal. I was the only one in the neighborhood who has the solar thermal water heater, domestic water heater, because I want to enjoy hot water during the shower or during any dishwashing, like, although it is not that much popular in Malaysia, but since I was in overseas for a long time, so usually we use hot water bath. So this we never want to use the electricity to produce hot water, okay, by some electric heater. So since north facing as having some hot water bath, I was lucky. In fact, if it was this side, I will be losing my space because this is for hot water. So hot water, south facing, north facing does not matter in Malaysia. It's almost same. But solar panel, south facing, north facing has a little bit difference. So I was lucky that the installer, the hot water installer, didn't do in this space. Maybe it was my instruction as well. Then in future, I want to put solar panels towards the north. This is south facing roof. So initially they planned to put this much 11 solar panels here, but since there was it was limited, so they put this way 6, 7, 8, 9, 10, 11. This way they put the solar panels. So on a fine morning they came, they brought the solar panels. Okay, these solar panels are standard solar panel. So it was English Solar. I think English. There's a company, Chinese company, but they have Malaysia. They have office here, or they have also factory here. So and in July they came with a huge crane because it is very heavy. You cannot carry. So huge crane. It took all the panels to the roof, like 3-story, because our houses are 3-story. 1, 2, 3, 3-story. It's quite. It's not 2-story, double-story. It is 3-story building, and they put the inverter in the corner where it is, like I said, no, not inside the house. They want to hack the wall, and they put inside the house. I said, no, just put outside. I'll put some enclosure and combiner box, inverter, everything is outside, but it is protected for any heating or something, any rainwater leaking or something. So it was really nice in that case. It happened, I think, in a day, almost done. One day it was done. And the other day they came to commission it. Okay, so they are measuring the what is the output, what is the temperature, and what is the tilt angle. So they're measuring with the sensor what is the total output energy. 1.22 kilowatt that time. It was very high sunshine that time. And the solar panels, you see that 1, 2, 3, 4, 5, 6, 7 solar panels. Although you see it's only one panel here. It's only one panel. So south facing, there are 7 panels, 1, 2, 3, 4, 5, 6, 7 panels, and north facing there are 2 panels, 2 or 3 panels. Okay. So altogether, it was not 5 kilowatt peak, it was 4.95 kilowatt peak. I mean, under the standard condition. So roughly 5, I can say, roughly 5, only 550, I think 50 watt peak less than 500. So it's okay. But the thing is, now I'll show you one by one. So how in the last 3 months, it is helping me. For example, I have an app in my phone, which is given by free, which is free SunGrow, which is the inverter maker, because inverter is the main interface. Okay, inverter is the main interface. This inverter is the main interface. Whatever DC current is coming, it will produce AC current, and this AC current will be transmitted through the meter. It will be transmitted to the grid through the meters. Okay. So inverter, I downloaded this SunGrow inverter app. So they show every day I can check. In the beginning, I was very excited. Every day I was checking how much I'm producing, or how much money I got, something like that. So this is even they put a picture of our house here. Okay, this is my my residential house, and with some number, identification number. So let me show you one of the example, like in a day. For example, it's like 20th of October. Today is 25th, right? 5 days ago. So how much it produced? Okay, almost. I have, this is almost like the day is over. So this is the production curve. You see that's huge disruption. It is not like a smooth curve. Why? Because in Malaysia, the climate, suddenly we get cloud. Within a minute, we get cloud. We get rain. So the climate is so fluctuating. I saw every day there is a huge drop. It is Malaysia is a tropical country. It's good for sunshine, but because of this disruption, because of the intermittency, always there is a fluctuation in the power generation. So first impression is that it is not smooth. It should be smooth. Like if it is smooth, we can get huge amount of power. In this case, 4 kilowatt. 4 kilowatt can reach. From this we can see that it goes 4 kilowatt. But because of the intermittency, so in a day, on that day, we got 19.6 kilowatt hour of energy. And total in the last 3 months, we got 1.8 megawatt hour of energy. It's the total until now, because I installed it on July the 4th. And total revenue on that day, on that particular day, 20th of October, revenue, this may not be right, 10 ringgit. Okay, for this, because the tariff, they convert in the tariff is 0.5 per kilowatt peak, 0.5 Malaysian ringgit. So they convert. Up to now, almost in the last 3 months, I already paid off 1/20th of the loan, okay, by this. In fact, more than that, I feel more than that. So this figure gives me huge satisfaction. Okay, one of the other thing I see that the power that I generated is equivalent to 99 trees I have sowed or I have planted, because I saved the world's carbon dioxide by that, because they are showing that you are producing electricity by the renewable energy, so which is equivalent to this much tree you have sowed or you have planted, and how much standard coal I have saved, because I'm producing electricity by solar panel. So until now, I have saved 735 kilogram of coal. I didn't use this much coal. If I didn't have the solar panel, I have to use this much coal for my power generation. So I also helped this way, right? So this is what the satisfaction is beyond the monetary thing. I'm saving. I am just accomplishing the carbon neutrality that is pledged by the country. Okay, so this is this kind of that I am showing again, and also month-wise. For example, the month of August. So roughly each day, 31 days. So some days are reaching. We can produce 20 kilowatt hour. Okay, like this one, 2, 3, 4, 5, 6, 7 days we got 20 kilowatt hour, and many of the days we got more than 16 kilowatt hour, and some days over 12 kilowatt hours. So there is it is good. If it's quite good number. In fact, if I say total how much in that. Okay, this is for September. Okay. See, I told you to remember 470. See, current month yield is 523. In August is 523. In September 513. Okay. In October, just now, October we have a few more days, but this is the data that we got. But still it will come. But what I say that if we look, we see the huge difference. Almost 50 kilowatt hour I'm producing than the estimation that was given by the companies. Okay, they said 475, but I'm getting 425, 525, 513. So it is more kilowatt hour than, because of because design was made by not in the location, maybe due to that one there's a difference. So I'm really happy that I'm getting more than what I should have put here, that the value that the same. But you see this one. Okay, 513, 523. Okay, so these are the value, and still it's come. It's almost 10 more days. Definitely will go up. This is the picture of the highest so far in one day. Okay, in one day, on this day, 4th of November, I got 23.5 kilowatt hour of energy. Okay, was sent to the grid. But again, you see there is fluctuation here, fluctuation here, fluctuation. Why? This fluctuation means our weather, Malaysian weather is so fluctuating that suddenly PV output drops because of the cloud coverage. Okay, although we have 12 hours of sunshine since morning, you can say that from 7 a.m. until 7 p.m. But the problem is it is not a full curve, it's not a curve, Gaussian distribution. We have huge fall during some of the climatic change, drastic climatic change, you can say. Otherwise, it could hit to almost like, I can say at least 30 kilowatt hour or more than that, okay? But this is also good figure. 23.5, it means almost like, I should say, for 5, almost 5 peak sun hour. Okay, that is quite good. Now, let me tell you, in Malaysia, okay, first 1 to 200 kilowatt hour, the tariff is ringgit 0.218 per kilowatt hour. You see, if you go up, the price is increasing. This is the electricity bill before solar installation happened here. Okay, so we are consuming too much of electricity. I should say we were consuming too much, like in some more than at least I should say 900 kilowatt hour. Okay, so if I see, I have 2 data here. One is the May before the solar installation. Okay, and after the solar installation, same graph. Before the solar installation happened in July. Okay, so before the solar installation, our price, electricity price was 858 ringgit. Okay, if you divide by 4.5, you can understand in US dollar. Okay, let's say okay, but now can you check? See, drastically dropped in July, August, September. The recent bill in September is 278. You see, if you just just see the 1/3, right? It became 1/3, roughly 1/3, right? So solar is helping me. I am saving almost 500 ringgit here, which I'm paying for the capital cost. So I have no extra burden, in fact, and I'll be owner of the solar system on my rooftop. End of the day. I hope you understand what I'm going to tell here. So before solar installation, I was paying roughly this, and after solar installation, I'm paying almost this. So 1/3, it came down to 1/3. It didn't go to 0 because we are a big family, 6 members. We are staying home all the time, mostly during the COVID situation. Also, so we cannot avoid it, in fact. Okay. Okay. With that, I'd like to conclude my talk, and I'd like to say my concluding remarks. First of all, grid-tie photovoltaic systems are also configurable. You can configure it, but according to your budget and according to your space and according to the vendor's availability, and also according to the contracts. Okay, the contracts available in your locality. Among the 3 main different kinds of standalone grid-connected system, grid ties are now becoming mainstream. Yes, people are putting rooftop because they know that there is no burden, like hidden cost or burden at once. So you can pay gradually. Okay, budget and space are the main constraints for the grid tie systems, but I think somehow it is solved because of the flexible payment system. Systems can be optimized according to the budget and policies. Okay, whether you follow NEM policy, feed-in tariff policy, or self-consumption policy, and also sometimes it may require storage battery in future, not in the beginning. So you can fit, okay, accordingly. Okay? You can check accordingly. So with that, I'd like to conclude this talk. So I hope all of you have enjoyed the grid connected system. Now it's open for question here, if there is any. Thank you so much for your kind attention.
Thank you so much, Prof, for second session. Actually, second session is also great for us because you show us why we should focus on solar system. Because if we don't know why should focus, so we cannot actually focus on implementation. So that's nice, and how it works, like compared to the nuclear power station, and also in terms of economy, how can it help us economically? Not only that, and also compare with other renewable energies and grid connection also, like if we have the enough energy, so we can sell to the government and we can back to it. And yeah, and also I have seen in your some slides that you talk about the power station, and you mentioned about 42. That means that it's not like if we install solar panel, so we cannot use other things, like we can do agriculture.
Yeah.
We can produce agricultural product because they will have enough facility because it's from top, so we can't see the gap. So in real field, it's a huge gap. It's panel to another
Yeah,
panel.
yeah, it's true. I saw in some of the places they are planting potato. In some places they are planting different things, but they just elevate a little bit, like 2 meter, 1.5 meters. So elevation, a little bit elevation is needed, and they are plowing the land beneath. So it is also helping, and it is, you know, it is a little bit cool. The place is cool because it is so, and you can produce different kind of like vegetables also. I mean, unconventional vegetables.
Because vegetable, the trees, they are absorbing the extra heat, so it can help to produce proper electricity from solar panel.
Yes, yes, exactly.
Yes, and also in my, because we are working in a Faculty of Environmental Management, so when we talk about SDG or green for sustainable world, so we all the time say that we cannot stop CO2 emission, but we can manage or we can control it. So from your case study, we can see that first when you before installation it was 800 around 900 ringgit, so it became a 250. That means that when you already saved 1/3 the price. At the same time, coal, and also we can compare with how much CO2 emission we can reduce from that. So if I think that if we think about long-term vision, like maybe after 20 years, if we do like this, so we don't need in future actually the air conditioning system, because when world temperature decrease, so we don't need to depend on that, and we can manage it.
Yes, yes, it's true. I mean, it's nice comment from you that whenever we take care of the carbon neutrality, we reduce the carbon dioxide emission in the air, so that world temperature will also reduce. So we do not need that much air conditioning system. Okay.
Yes.
Even even the room I'm sitting, in fact, because I have rooftop solar, so I do not need, even I'm deep mid-noon here, I don't need a air conditioning system because my rooftop there is a solar system. So my roof is also covered now by that solar system, and the heat is somehow, it is not the direct heat coming to this place.
Yes.
So I'm last 2 hours, like since 11 o'clock, I'm sitting here. I didn't use the air conditioning system in this room. But if there was not solar panel, maybe it will be very, very hot because it's direct heat. Now the solar panel, now these solar panels are taking care of this. I'm just sitting beneath this space, in fact.
Yes, Prof. And also from your slide, we can see that Malaysia, they have a focus on not only solar panel, they are focused on hybrid technology. So if we like in the nighttime, maybe we can rely on other renewable energy like biomass or wind turbine. So because we cannot, that's the truth that we cannot like depends on only one technology or specific one energy. So if we combine together renewable energy, so then we can work, we can reduce the CO2. Like nighttime, we can use the hybrid system. You already mentioned about smart grid hybrid system for wind turbine or maybe other renewable energy. So it can help us to stop the CO2 emission.
Okay. Any other question?
No, coach. I think from audience, any question? From audience? I think from audience, they don't have any question.
Okay.
So you can stop sharing, Prof. No problem.
Okay.
So we also almost at the end of our session, and thank you so much, Prof, for your wonderful session. I will share this recorded video with our other colleagues and will present to our university. And thank you so much for your time. We know that you are sick, but we give us time.
Suddenly, I'm really sorry. I was having suddenly flu and feverish feeling since morning. So I'm today I'm a little bit sick. Still, maybe I have a little temperature, but because since I do not want to disrupt the schedule, so somehow
No, it's okay, Prof. So we are sorry to.
No, it's okay. It's okay from my side.
It's a 4-hour session, so thank you so much, Prof, for your wonderful time.
Thank you, everyone. any other time you contact me, okay? Any other time for any kind of thing. The audience also, please contact me. I think you can get my email address, or for any kind of it's related to the research or all those things, you can contact me, and you can get my email address. I think I gave my email address towards the end of the slide.
Yes.
You can see the email address there. Okay. Thank you, Mr. Shahriar, once again.
Okay, Prof.
Thank you.
See you 2nd November, Prof.
2nd, right? Is it 2nd or
2nd November?
Yeah, 2nd November.
It was first, but we should
yes, 2nd. Thank you. Thank you.
Thank you, Prof. Thank you so much.
Thank you. Salam.
Salam alaikum. And thank you so much, all of you. See you.